Hello everyone, welcome to the live stream. How you doing? Let's just set some water. Hello and welcome. Hi there, and today, hi there Ash, how you doing? How you doing Ash? Okay, today, hello everyone to an audience of one person. Oh, come on. Just, come on. Can't even say hello to an audience of one person. Ridiculous. That's how I always start. I also end with, thank you everyone so much for watching, even though I am damn well that most people don't go to the end of the live streams or videos. Okay? So don't you dare. This is what we did last stream, by the way. Just as a gentle reminder in case somebody forgot. Okay, I am fully aware that there's a lot of noises happening in the background, but I promise I can explain. First of all, let's move this. Let's move the pipe as well. I'm doing good. How are you? I am incredibly unstable. I don't even know why, I'm just incredibly unstable. I'm hoping this will help. Oh, that smells like dirt. Yeah, that does. Hi the dog, how you doing? I got the new coffee press. Since, I'm no longer drinking the toxic sludge. I thought I could use a coffee press. I don't have a coffee machine because, well, those are expensive. But I do have a coffee press, so. Alright. Would you look at that deliciousness? Just straight up yum. It might actually be a bit too much coffee for the amount of water, but brilliant way to start the stream. Can I sponsor you for my entire bank account? There's about 500 euro in it. I'd rather you didn't with your entire bank account. I'd rather you kept some of the money in your bank account for yourself. Lord knows I should have done that. You know what's funny, everyone? That's a minus sound. Oh, I see. Well, in that case, I would rather not even more. -5. I see. Okay. Yeah, I'm starting the stream this time with making coffee because I actually planned for this to be a bit of a longer live stream, and that's because yeah, absolutely not giving it any time to settle, am I? Oh, whatever. And that's because we actually have quite a lot of work to get through. So let me just bring you back to this screen. Okay. So and such and such and so. Whoops, no. There we go. This right here, yeah, I did select solid state chemistry myself because I really wanted to go on solid state chemistry, but the poll is in. And consider me shocked and surprised. Particle Physics 1. So we'll be working on a video about particle physics. Also right here below that, that's a video that's Patreon only, so unfortunately I can't share that with you right now. Is the image in the new YouTube post from the studio? It is actually. I have a couple of them and they're all quite brilliant. I like them a lot. I think they're comical. Hold on, let me... It is from the recording session I did for the video. I also got some photos done. Looks like a Patreon said organic chemistry. Yeah, I wouldn't be surprised. I mean, it is organic chemistry after all. I mean, look at this. Make it 28 JPEG is certainly... It's certainly an image. Particle physics, where you tickle physical parts. No, it's whether you tickle physical parts, obviously. Duh. We all knew it. Anyway, today we'll start the work on that video actually. Also, we'll need to work on another video in the background, and I will actually need to work on 3 videos at the same time. But it's fine. It is fine. Because first things first, we're gonna go into physics, and we're gonna find ourselves some kind of source for the particle physics. Now, I already looked into it a really long time ago, hence why I remember, there we go, that there were some books on the topic. And sorry, Beams, you're looking good in the suit. It goes well with your mask. Thank you, Doug. I think so too. I think as far as all the different types of attire go, it really captures that supervillain vibe, doesn't it? There's really something about it. I am just villainous. Alright. Nuclear particle physics. Yes, that would be ideal. Let me just... We'll need... Actually, I would like to do 2 things. Laboratory research, maybe I can do resistance. I don't know if we'll get through that much research today, Ash, actually. Because I have a lot of things to do. And when I do mean a lot. I do mean a lot this time. First things first, something that I haven't done in a really long time. But I feel like I need to get back in the habit of doing is a productivity tool. I used to make a lot of these for myself, and then I stopped because I went through this whole thing where, you know, I didn't want to be too much of a workaholic, yada yada, boring stuff. And chapter 8 is strong interactions. It's not gonna be fun. Oh, I like this graph. I do like this graph. Yeah. You have strong interaction that only works with quarks. Quarks will work with every single kind of interaction, and they also have mass from the Higgs boson. Photon doesn't actually couple, and gluon's not a couple with the Higgs. Higgs with itself is brilliant. Why are the loop-de-loops on themselves, actually? I would need to ask Remco about that. Remco was brushing his teeth at the stream, so... After this being like in the back 3 hours now, so yeah, it runs. Alright, I get it. Important stuff, trust me, I understand. Okay, hold on. Before I get roped into this, I first need to set up a render. And that's because I'm still working on the video. Believe it or not. Still not finished. It takes such a long time. Well, obviously not finished, but the first chapter of the video. No, this is gonna... Hold on, because I kind of messed up something. Alright, I see what the error of my ways has been with this animation. So I need to fix it by doing 180 to 1200, and then take all of these. And ideally put them all on a single line. There we go. Hi, the caper. Can't spell particle physics without part. Yeah, can't spell without article. Well, caper, we are doing particle physics because. Oh, did I already turn it off? Oh, dagnabbit. Hold on, I already turned off the page. second. There it is. Particle Physics 1. Yeah, democracy. Can you believe it? We actually did a democracy. Democracy worked by design, outcome 1. Yes. Only one person voted for the states of matter, because I personally voted for solid state chemistry. So yeah, that's why particle physics. But first, I need to get on this. Let's do y0, and let's put all of these on y0 as well. Alright, oops, absolutely no alignment. If I move the camera to, hold on, let me first get rid of the volume. If I move the camera to 0, 0, will that be too much movement for a single frame? Actually, not bad. 180, then individual, negative 180, then keyframe. Okay, now this is wacky. But the reason why it's wacky is because, yes, these rotate twice, so it should be 180 here instead. There we go, and now the movement should be much more fluid. This is just a consequence of how rotations work. No, it's just still flipping over. Stop that. Oh no, it starts with positive. Positive, 0, negative. Oh, damn it. 100, 0, minus 180. I am an idiot. That's, wow, irony. You don't see that often. Pure irony of trying to fix a problem that doesn't exist and causing the problem to happen. Incredible. There we go. Did you contact any international science union yet? I am getting ghosted by absolutely every, well, not every, but by vast majority of people I message, I get ghosted by. So far my statistics when it comes to this whole thing are not great. That's negative 3? No, negative 5. Yes. And then right here will be 5, 3, 0. Not negative 0. We don't want negative 0. Alright, brilliant. Brilliant. Yeah. But anyway, there we go. There's the animation, which means we can get to nuclear particle physics. Let's just see what the textbook is about. Let's see if it's a fit. Nobel Prize in particle physics. Is the Remco there? No, I'm not interested then. Timeline of particle physics, right? Stages, fission, fusion, low energy nuclear. We're not really interested. Are we interested in nuclear? We might be interested in nuclear. No, nuclear physics is going to be a separate being in this case. Quantum chromodynamics. I mean, this is like introduction, but I specifically don't want to be stuck in the introduction, which is something that happens a lot. Wait, I'm sorry, hold on. Extraterrestrial particle physics? What do you mean? Alright, no. Second, accelerators, targets, main experimental facilities, detectors. We're not interested in practical aspects this time. Experimental facts, interpretation. This is all nuclear. This is mainly nuclear. Which is tricky. Because... Oh, never mind. I just turned off the book right before the chapter that actually goes into what I want. I would need Remco's help on this. Oh, that coffee is bitter. But I do believe that's just the Feynman, like particles. No, first interactions, then particles, then Feynman could actually explain it all. And I think that's a good idea for the video. This would be like pretty solid. So, particle physics. First interactions, then particles, and then finally Feynman diagrams. Yeah, shut up. The F-man diagrams. If only you posted 1 hour of Danny noises to start your work too. Danny is almost done, don't worry. Danny is almost done. Let me see how long Danny has. 9 minutes. Can we do 9 minutes? Because Danny is almost finished. I do apologize, but before the live stream I did print the entire mask skeleton because I was lacking it ever since I updated it to the newer version, so that is unfortunately we were lacking. F-man, the physical Bernoulli. The only one I'd have. What do you mean? My car technically? What? Ash, I am way too sober for this. Okay. Ooh. Okay, brilliant. Interactions we obviously have. Gravity, just as an example of what an interaction is, we won't actually get into gravity because it's really difficult to tie in gravity to particle physics. Actually, it's mass, doesn't matter. Then we're gonna have strong electroweak interaction. And I ironically like the sound. It has a futuristic touch to it. I like it as well. It's a very nice background noise, I can tell you. When you're working on a video, when you're working on a script, these sort of printed noises are just really lovely to just have having in the background. Don't mind if I just go that way, so this one real quick. Okay, gravity. Second would be electromagnetism. Then it would be strong interaction, and then it would be weak interaction at the end. For particles, we would start with quarks, I believe. That's the best way to start, correct? It's got either do as well, something. A lot more time to get ready for any form of social interaction. Alright, fair. Alright. Quarks, fermions, bosons, and the Higgs has to be own because it's just wacky. And then last, Feynman diagrams. Wait, damn it, I always confuse fermions with leptons. I'm an idiot. Leptons, not fermions. Okay. Brilliant. Basic concepts of theoretical particle physics. Let's see. What are the basic concepts of okay, difference between relativistic and non-relativistic mechanics. Hi there, Remco. How you doing?
Physics. I appreciate the physics.
It is physics. That's because I did the poll on Patreon on what the next video should be about, and Caper won with particle physics. So I'm gonna be doing physics. Yeah. Hell yeah, indeed.
I will be awaiting questions if you have any.
I will have so many. That's because I will have so many. The entire last chapter, the structure of the video will be fundamental interactions, particles, elementary particles, and then just Feynman diagrams.
Ooh.
Because I just feel like that explains it pretty well. Okay, do you want me to like compile a list of questions, or do you want me to just ask them on the fly?
when you have questions, just hit me up. If you're streaming, I'll just join in the stream.
Oh no, well, I mean, because you're already here, like, in that case, obviously.
Yes, but I'm not gonna stay very long for now because I've headaches.
Oh, it's fine then, it's fine. Okay,
So
I'll have a
just
file.
like if you have questions, either ask the question or ask me to join stream.
Alright, alright. Welcome, Chromium
Or we
first.
can-
A complex thing, Flame, I think, is the person you should go with this, because this is about electron configuration.
Yeah, this is like applied physics. I can't help with
This is
this.
borderline chemistry. Actually, hold on. Chromium electron configuration. My guess was that because of spin alignment, they will have the same spin value, but
That I already went wrong by reading Chromium 3D. I was already thinking of a 3D system, but it's just shell D something. I don't even know how the shells work. Ash, I have headaches now. This is probably why.
I'm sorry. Wait, hold on. Is my internet dying?
You were gone for a second, but I can hear you again.
Oh no, I just wasn't saying anything for a second. But is my internet dying? Because you are mixing right now, right as DuckDuckGo isn't working for me. But the stream connection is a perfect 6 kilobits.
It's where all the internet is going.
There's very specific
And-
kinds.
Ooh, Faven diagrams. You should only do introduction to Faven diagrams, and the next video will be a very detailed video about Faven diagrams.
If I had to make, I would need to make a dedicated video. If I actually want to touch one.
Yeah, just Faven
It's
diagrams.
just to me, like, you know, Feynman diagrams is a very nice way to just nice combination point of particle physics because well, I mean, just fucking look at the diagram, am I right?
I love them.
Feynman diagram.
Well, you can do an entire video on the Faven diagrams. I have enough material.
Yeah, but well, like,
Working.
like what is that? Particle physics. I am hold on. I'm laughing a little bit, maybe with my repeat is not quite as funny, but like particle physics, the whole name comes from you're trying to figure out what is the physics on particles, and then like you have a diagram which literally shows you what happens. It's just,
This is the physics of This is the physics of interactions. What can I say?
this is really good. Is it possible to have different spin? Oh, that's a way more difficult of a question, complex thing. You know what? I can message Flame if you'd like. I mean, you could too, but hold on. Flame.
Summon the British.
In Chromium. Hold on, let me just first playblue.com. Electrons. Chromium. Right, yeah. In Chromium. The electron in the 3D and okay. The electron in 3D and 4S have the same spin value, and also can you have different spin values for them? How convenient it is to just not have to think and have other people who know this stuff. Okay, one key people particle is that special relativity principle. As we all know, the catalyst with no relativity. Of course, people attempted to generate equations for diversity reasons from the equations. There are two such equations. One declined golden and the one hand Dirac. National equation of particles, just what we do is equation right. Okay. Skin estimate of the non-relativistic energy momentum relation equals 1 e squared. Since time delivering plane, derivatives. Okay. Natural extension would to use the relativistic energy expression. Okay. This is a nonsensical equation. Unless we specify how to take the square root of the operator. First time is a problem going on. Oh, is this the problem of two solutions? Wait. Is it?
Yes.
Yes, it is.
But also a problem if you want to solve it, because if you want to solve it, you will find that you can express it as a Taylor expansion, And this is just bad in the sense that everything will depend on, or something will depend on every point in space, so it's very non-local. Horrible.
Okay. I see.
But
I don't think I've heard about the Klein Golden. Okay, Danny is not there, no more annoying noises in the background. This is an extended equation of spinless particles, or spin 1 particles, bosons, but not describe fermions, haven't just spin, since there is no information about spin is the equation. This needs careful consideration. Spin must be an intrinsic part of the relativistic equation. Dirac realized that there was a way to define the square root of the operation. Trick used to define the four matrices, alpha and beta, have a property that is square one, the anti-commute. It's a question in your words and very well behaved. Mu and physicists are running out of clothes, so they need to expand their tailors. And with that message, Ash is going. Alright, bye Ash, have a good one.
Hi, Ash.
Brilliant message to end on. No, the minimum dimensional matrix of is a full vector. It's closely related to these particles of spin. As a vector equation a bit further, one possible forms alpha and beta is. It's a 2x2 poly spin matrices. I read about it before and I understand about as little as when I read about this the first time.
Harley spin matrices are just matrices to describe rotation.
I mean, no, I have used these.
Yes.
So as far as the eigenvalue equation, right? Eigenvalue gets solved with my equation. This. Oh. Oh.
Do you see what I see?
Equals positive. Oh. And seem to know particles spin up and spin out. Holy shit, that was like a whole hobbit's worth of a journey. You shall study antiparticles positrons. Oh my goodness. That was like a whole Hobbit trilogy worth of a mathematical journey. Just as photons are the best way to analyze, decompose the electromagnetic field, electrons and positons is a natural way to decompose the Dirac field. That is the general solution of the Dirac equation. The analysis of a solution in terms of the particles it contains is called, in second quantization, and just means that there is a natural basis in which we can say there is a state at energy E which is either full or empty. This could be correctly referred as occupation number representation, which should be familiar from condensed matter physics. This helps us see how a particle can be described by a wave equation. There is a remaining problem, however. The Dirac C, correct?
Yes.
Okay. That is... Well, I'm not gonna be lying. I don't blacked out here, but linear algebra is not my strongest of suits. I'm not a mathematician.
You can just assume they're right.
I trust them, yeah. I mean,
Yeah.
you know, Niels Valet, I trust him.
100% credibility.
Valet, holy shit, actually. Nuclear and particle physics. This is his nuclear and particle physics book. But I actually, where is it? Use his quantum mechanics book for my videos. There we go. I knew I recognized them, yeah. This is actually the same person that I use as a source for my quantum mechanics videos.
I see.
I mean, it makes sense, I guess, that the person who
Yeah.
writes my quantum mechanics writes about particle physics, but okay. So this makes sense.
If you want more material on why the square root is horrible, do hit me up. Like I can't present it right now, but I can like.
That might actually be important later on. But first, hold on, I just need to recap, make sure I understand. Basically, actually, could you do like a TLDR for now? I'm curious what.
Yes.
The Taylor series, right?
Okay, go up.
Yep.
To the beginning. Alright, so we have this Schrödinger equation, blah blah blah. We want to be able to describe a relativistic particle, and the usual way of doing that is by Einstein's equation, dispersion relation. But this gives a square root, and this is horrible. So we need to find a way to deal with the square root, and that is basically what we're doing in this whole section. And one way of doing that is just squaring it. This gives the Klein-Gordon equation, which is just a wave equation. Another way of doing it is is increasing the dimension of your system. And this whole procedure, takes some algebra as you saw, leads to a four-dimensional representation of particles where you can describe spin in terms of two. This is the equation here at the bottom, like entirely at the bottom, a little bit more down. So you can explain, just the two vectors at the bottom. You can explain a particle in terms of these four vectors, and different entries of these vectors just describe different spin states. So not only have you described the relativistic particle, you also included spin in that. You found spin in that.
So that's why it's up spin or down spin.
Yes. And now you will also see that, oh, hey, we have a four-dimensional object, but somehow the spin operator for a particle acts only on two of those, because the other two entries will be for the antiparticles. And this is your first introduction to a spinor now. You're welcome.
Okay, then one question, because, all right, I'm doing this for video, let's be honest. So I unfortunately am looking for like a way to, in simple terms, put the problem of the square root, because I always understood it as you get two solutions, but you said that more importantly is the Taylor thing.
Yeah, it's non-local. But
could you elaborate on that?
Yes, but I will need my research. Because I know how roughly how to do it, but I don't want to speak mistruth right now.
No, it's fine, it's fine. That's my job.
That is your job, okay. So.
And in the meantime, we're looking. It's basically like a different way to state the quantum fields, right? Where you effectively end up with a field where each point has a value, and that will be your particle. Like, is that also what it implies?
Wait, oh, you were asking me.
Yeah.
Ask the question again, please.
So this also at the end of this entire like procedure, this also like once again reaffirms the quantum fields, as in you have a field where each point has a value, and that value would be your particle.
Yes, I think if I understand your question.
Yeah, so what I mean in this case
yes,
is that these vectors like describe the spin of a particle in a field, and hold on, I'm struggling with wording it as well. I mean, right here it does say that quantum mass behavior to decompose the electromagnetic field. Electrons and positrons are the natural way to decompose the Dirac field. This is general solution of the Dirac equation. Second quantization. Yeah, so I feel like this actually also answers what I'm asking. So effectively, this is like reaffirming the quantumness of quantum mechanics, that it's quantized fields.
Yes, but so far we're not talking about fields yet.
Yep.
There is that, like, you will see fields probably in the next or the lecture after that.
Let me see, antiparticles.
So there is no such thing as like, oh hey, this is a field.
That's why I always thought of it as two solutions. This is the exact book. Oh my goodness, this is the book I've used last time.
The book.
Because I remember this, yeah. And so, Dirac equation has nasty property. Since the relativistic energy is quadratic, both equations have, for every possible energy solution, a negative energy solution. We don't really wish to see such things, do we? Energy is always positive, and this is a real problem. The resolution is surprisingly simple, but also very profound. It requires us to look at the problem in a very different light. Yeah, exactly. Oh, we have the Dirac equation for free particle. It has positive energy spectrum starting mc squared. You can have a particle at lower energy, but also have negative energy spectrum below negative mc squared. Expression is positive energy state is natural. Each state describes a particle moving at energy above mc squared. So we can have negative energy states, and the expression is very different. Simple. We assume that in an empty vacuum, all negative energy states are filled, the Dirac C. The excitation relative to the vacuum can now be obtained by adding particles at positive energies, creating holes at negative energies. Creating a hole takes energy, so the hole states appear at positive energies. They do have opposite charged particle states, and thus would correspond to positrons, and shows the great similarity to the behavior of semiconductors. We know the situation in figure 5.2.2. Hi the class, what are you doing? I'm learning particle physics. Yeah, we're gonna start doing this because why is it so dead? I don't know.
They're sleeping, even though that's not allowed.
The channels I interact with aren't dead.
Aren't we all? That is such a...
Yeah, we've all been there. Let's be honest, we've all been there.
This is the point where you just sat in life and you just go study particle physics.
We have all been there.
Midlife crisis.
Many immeasurable quantities become infinite, and we are only interested in the finite part, reminding after removing the infinities. Sentences uttered by the utterly deranged.
I mean, to be fair, this... Wait, read the next sentence as well.
Yeah, I know, renormalization, I know.
This renormalization, this was introduced in like the last class of my QFT. That's how advanced it is.
You mean last? Holy shit, that does not bode well.
Let's just say it's a lot of mathematics and it's a lot of
I always thought of it. I mean, listen, I'm not a particle physicist, so I'm painfully aware of that. That's why I like in my head. That's why I need to oversimplify these things myself. Like, you know, the square root of relativistic energy being an issue of Potter solutions. But so to me, I always oversimplified in my head renormalization. I imagine it like just limits of, you know, when something tends to infinity, you cannot solve for infinity, so you just take a limit as tends to infinity. That's how I always thought of it. How? Okay, I know. Alright, I understand.
normalization.
I understand you probably wouldn't have the time for it right now, but how do you actually renormalize?
Oh, it's actually very easy. If you just need to know the concept of a Lagrangian. If you have your Lagrangian, you do know Lagrangian, right?
Vaguely, big L.
Just potential minus kinetic, or kinetic minus potential, whatever. Minus signs don't matter. The Lagrangian is that whole massive
big L
equation.
Or am I thinking of something different?
The big L, yeah. The fancy L.
Okay, yeah, then I know Lagrangian, yeah.
The whole thing is this describes the system entirely, the Lagrangian. So if you want to find the equation of motions, just how particles behave, you will find in classical quantum field theory, you will find some infinities. The reason is you need to integrate over momentum and this diverges. But if you add some term to the Lagrangian, or subtract some term, like a very specific term, then these infinities disappear. So you can find this term by like starting with your original Lagrangian, working out the infinities, and then adding a term that exactly counters this infinity. It's so crazy to me how that works. It still doesn't make sense, but it somehow makes sense.
Sentences uttered by the completely deranged.
But like, how do you justify cancelling out an infinity?
I mean, like exactly. That's exactly what I'm saying.
But then if you do the entire thing again, if you like add something to your Lagrangian, to your energy function, and you calculate your equations of motions again, and then you will find that this infinity is no longer there. So everything works. So the only iffy thing about it is that if you do so, then you'll also add a small contribution to the to the mass, and this is the whole concept is known like bare mass.
Free chapters done. Okay, but that's okay. That's another chapter about randomization. One of the key features missing in discussion above is the fact that all the pictures I have drawn are infinite, somewhat of a severe blow. The key point is to understand that this is not a problem, but has to do with a misinterpretation of the series. When you introduce the alpha and E into our theory, we use the measured value of the charge of an electron, which is a solution to the full theory, not to artificial problem with all vacuum fluctuations turns off. What it means is that we should try to express all our answers in physically sensible, measurable quantities. Renormalization is the mathematical procedure that does this. A theory such as quantum electrodynamics, right? I don't remember. It's called renormalizable if we make all expressions finite by re-expressing them in a finite number of physical parameters.
Yeah. That is what I was saying at the end. Like, if you look at your variables, like your mass, your charge and stuff, they will get a contribution from the renormalization, and this contribution ensures that it's exactly as we measure it. So it somehow is. It's not that confirmed because I don't think the confirmation is as rigorous. I'm not too sure on that, but somehow it seems to work out exactly as like this whole canceling term. It's required by nature.
I mean,
I don't like it.
It sort of makes sense, I think.
No, it doesn't.
I mean, it's particle physics. What makes sense in here? Listen, the book starts with like it has different like images for each chapter, and I like in the history of particle physics these I don't know what they are exactly, if they are interactions or couplings. I'm guessing interactions, but like the gluons, weak bosons, and Higgs boson looping in on themselves is just something I like about it.
They can self-interact.
Normal, you know.
You can have a Feynman diagram with just 3 Higgs bosons.
And we just accept that. It's fine, whatever.
Yeah, because
what website are you using? I'm using LibreText. Absolutely brilliant, and I love it. Free books. That's why I like it. I use it as sources for a lot of my heavier videos. Because it's I like it a lot.
But if you want to have the reasons why the square root is bad, first of all, time and space are different. Momentum is basically, from quantum mechanics, you should notice that momentum is basically the derivative to position. Actually, go back to that equation. Show me the equation.
Okay, hold on.
Helps with the talking.
I'm opening up so many pages, but give me a second, let me just... this was the difference between relativistic and non-relativistic. This?
Yes. Yes, they already say it here. The second line, the momentum can be expressed in terms of h divided by I times the derivative to position. Or, well, nabla, however you want to. So, in this equation, in this square root equation, you see the momentum. This is a second order derivative to position, and this is under a square root, whereas the time derivative is not under a square root. So there is already some funky going on, because you want, in relativistic mechanics, you want all space and all time components to behave exactly the same, because that is what defines relativity. So that's already one sign, that's why it's fucked up. Another sign is if you, because the speed of light is like a huge quantity, so if you take it out of the square root, you will have one, if you will, how do I say this? You'll have one of the terms will be like something divided by c squared, which is in this case the momentum. And then you can Taylor expand on that. You get an. I can show you this. I can like write it out so it makes more sense later. But you will get an expression which is just 1 plus. mc squared plus 1 over 2 mp squared plus leading terms, and this means that the momentum acts like with infinite amount of powers, and this is very, very bad.
I imagine.
Because this just means that if you have like a point in space, just having the normal momentum doesn't suffice. You will need some extra kind of information to ensure that your particles are doing what they want. And this extra amount of information is an infinite amount of information. Not very fun. I can write this out so it's more clear. But it's very crucial as to why the square root is horrible.
Okay. Oh, this is... Okay. It's... I don't think I get it, and I don't think I can get it on the fly.
No, it's fine. I will write it down, and then you will get it.
By the way, Fake Octopus said, I am already loving the guy with the thick Dutch accent.
Banned.
Yeah, I know, I am incredible. What do you mean banned? They're obviously referring to me. Me and my famous thick Dutch accent. Yeah, that is my physics expert, whom I utilize for physics.
I take Fake Octopus. You're also Dutch.
No, no, I know where this leads.
What do you mean? Surely I'm not going to talk in Dutch.
Oh no, not that. I'm talking about the image. Some Feynman diagrams for dressed propagators.
Oh yeah, this is just corrections to the propagator. By the way, this is if you see the green loop in like on the bottom, one of the green loops.
Yep.
This is where the infinities are coming from, because you are like this green loop just represents momentum from some particle that like comes back to itself. So you have an integral over momentum, and if you have an integral over just a single linear component, it always diverges, as you know. Integral over x is from minus infinity to infinity is divergent.
Yeah, I know.
So horrible. This is exactly where the infinities are coming from, and this is why we need those counter terms, because we need to do something about this so that it isn't the infinite anymore. And now the funny part is, if you do that, if you have that counter term, then the green loop will not contribute an infinity anymore. But any higher orders, such as the diagram below with the blue, the photon going, like interacting with the green with the green loop, it will also not give a contribution anymore. So not only did you solve one order, you solved all the orders just by one contribution, and that is very impressive.
Wow.
It doesn't hold for every quantum field theory, but it holds for like the main quantum field theories, such as electrodynamics.
Okay, hold on. Let me have a read on this. The great problem is in understanding the meaning of virtual particles. Suppose we are studying the vacuum state in quantum electrodynamics. We wish to describe vacuum in terms of states of no positrons, electrons, and photons in a vacuum. Since these particles interact, we have short-lived states where electron pairs and photons and just dots, very menacing, appear for a short while and disappear again. This is also true for real particles. A real electron is bare electron surrounded by a cloud of virtual photons. A photon can be an electron-positron pair the same part of the time, and more such anomalies. So in this case, this is the bottom diagram. Am I answering that properly? The bottom diagram...
I'm getting ads.
Yeah, we're getting ads. Hold on, I can give you Discord. I'm sorry, I get the wrong thing. There we go.
I love YouTube.
Alright, so if I'm understanding this correctly, the bottom diagram is a photon into an electron-positron pair into a photon.
Yes.
Okay. And
but wait, are you talking about the bottom or the one above that?
No, I'm talking about this.
What you described is the middle one. So just the one loop.
Yeah, but I mean, in this case, this is just going. This is like all the possible amounts that this can happen, right? So just photon to both particles, to photon to both particles, to photon to both particles, to photon. Or am I?
No, in this case, the bottom one describes how. Once again, what I said yesterday is the most important thing is the initial and the final state. So in this case, you start with a photon, you end with a photon. And all the ways you can do this is by just considering a photon propagating, a photon that creates a particle pair and then annihilates again and becomes a photon.
So wait, is this like a superposition in this case?
Yeah, but you can think of it as superposition. This is all the possible ways of starting with a photon and ending with a photon.
Oh, yeah, that makes sense then. So, like, starting with a photon and ending with a photon is equal to just the photon, or photon to particles to photon to particles, fucking brilliant. Photon to leptons to photon, or photon to leptons to photon to leptons to photon, and then you add all of them together because these are all the possible.
Yeah, and like the whole thing in like if you do the quantum field theory is the photon propagator will give the main contribution. I guess you can see it. Yeah, you can see it as like it's a big number plus a small number plus even a smaller number, and that just keeps going. The more, well, I guess interactions you add within the whole thing. Mainly because it's like, yes, it's more unlikely that all this stuff is happening in between. Like just for a photon, like for a pair creation, that's unlikely to happen. It's even more unlikely to happen that you have a pair creation that interchanges a photon between them. So the pair interacts with the photon and then annihilates again. And it's even more unlikely that if you have like a pair creation that somehow interchanges a photon and this photon also undergoes a pair creation. Like that's all the stuff that theoretically can happen, but physically they will like not happen. But they still give a non-zero contribution.
That makes sense.
Yeah, and in this case the whole problem is that if you add all these, like they're all finite numbers except for some. Thank you, self-propagation. If you add all these, it also needs to converge. And you know, it doesn't always converge. If you have 1 plus 1 over 2 plus 1 over 3, that sequence does not converge. Even though the steps are getting smaller.
So wait, if it doesn't converge, does that mean it's impossible, or what does that mean?
No, it just means that our physics is stupid enough. We don't know how to.
I see.
Physics theory is not useful. Like we can't say stuff about the system anymore.
So the bottom one makes sense. What about the top one? Because the top one, that would be like some kind of lepton, right? And then that lepton.
Yeah.
So if you have a lepton, then that could either mean a lepton, or, and in this case, what is happening here? Like a lepton emitting a photon and then absorbing it?
Yes.
Oh.
Once again, the whole thing is you start with a lepton, you end with a lepton.
No, then that makes sense. Yeah. Okay. As I have sketched above, Feynman diagrams can be used to describe what is happening in these processes. These describe the matrix elements, and the actual transition probability is proportional to the square of this matrix elements. So one can show that each electron-photon coupling vertex is proportional to E, and thus in each square, each vertex gives a factor of E squared. Actually, by drawing time in the vertical direction and space in the horizontal, schematically of course, we can see that the two possible couplings of the photon to matter, I'm not even gonna attempt to pronounce that, and pair creation are one and the same process. Still, it helps distinguish none of each vertex charge is conserved as well as momentum. This can be equally equivalent to dimensionless quantity approximately 1 divided by 137. This is so comical.
Yeah, this is the famous number, 1 over 137.
This is so idiotic. Like, all of these... Meaning, yeah, just...
I don't see the problem here.
meaning, the actual number of the meaning of life. We should expand enough around these questions. Expression parameters being unphysical cannot have dimensions. In other words, simply carry through this one amount of quantum. Smallness of alpha, we normally consider only diagrams as few as possible. Let me list 2 diagrams for electron-positron scattering, both proportional to alpha squared, as given in figure 542. Alright, let me. So, time, space. Which means that, effectively, this is just like 2... Right, so this is effectively... Oh, wait. Because they are... Because X is space.
Ash, that is probably the case. Except now you also need your paths to like split into, and they also have rules, so it's not entirely true. But yes, you will probably need a mode to be. I hate that word.
Hold on. So, on the right, this is effectively a... Wait, why are the arrows both going this way? Hold on.
Don't look at the don't look as much as the arrows. The main important thing is the time direction. Just look at time.
So in this case, it is just an electron and a positron annihilating each other, and then a photon.
Yes.
I don't know what the opposite of annihilation is. I forgot. Doing the opposite. Creating. Oh, that actually really is it creating?
I mean, it's annihilation and creation, so.
I was expecting something just comically fancy. I don't quite. Is the one on the left this? No, it's not the same as on the right. Is it?
It's not the same process, but like, think about it. What does this process represent?
Because what's screwing with me is that there is actually the position dimension in this case. So that would be like a positron and electron repelling each other.
Yes, exactly.
Wait, really?
Not entirely repelling, but yeah, it's just the exchange of a photon between 2 electrons, or between an electron and a positron.
Oh, that does make sense actually. Diagram change scattering change conversion can consider higher order diagram. So in this case, there is just the time. Oh, wowza. Okay. Now this one is rough because.
No, this is exactly the same as the
because
repulsion.
Because of the thing on the very top.
Yes.
Oh,
so
my goodness.
Technically, this left-hand side diagram is the sum of all these diagrams with all the different loops and different.
That does make sense.
Orders.
So it's like a superposition of everything that could happen.
Yes, and now they just draw the second order, I think, the first order actually.
Oh, I like that. I do like that actually. I do like that.
So can you, like, if you had to draw the first order for the other diagram, I suppose that is a very easy question.
Oh, wait. Repeat the question?
Go back to the second diagram, like the annihilation and creation.
So
what would the first order be?
Would the first order just be this, or would it, or is
no, that's the zeroth order.
Okay, that's the zeroth. All right, hold on, let me bring up paint. There you are. There's my boy. Well, I imagine then, if this is the zeroth, can I just skip the arrows?
Yeah, of course. Like the whole thing is there.
Then
statement.
I imagine right here it would split to electron-positron pair, and then it would go back to photon like this.
Yes. And then can you draw an extra order?
That would be like this, because then, right?
Yes.
And then an even extra order would it be like so?
Yes.
A Pokeball.
I mean, I kind of see some resemblance of melanification in here.
I was gonna ask that actually a while back ago, because like...
Yes, it's exactly the same.
The reason why I did the groan on the very beginning, like, oh, is because I saw the melons. And I just couldn't even...
I mean, in this case, it's not melons, because your interactions are 3-point interactions.
I just saw red leaves. Alright, Infinite Zero, yeah, the predictive power of QED. It's hard to say theory has predictive power without comparing it to experiments. So let me highlight a few cases of quantum dynamics. One of those so-called G factor of the electron related to the ratio of the spin over the contribution magnetic moment relativistic theory of the exact equation shows that G is equal to 2. The measured value differs from 2 by a little bit. A factor we account for in... Oh, that is close. That is wacky close. Of the errors in general. In theory are related to our knowledge concepts H bar and require better input. So as big as quantum chaos, strong interactions will be playing a role. We are approaching the limit. On the O, by the way. But yeah. So some of the errors in the theory are related to our knowledge of constants such as H bar, which means we effectively need to build a bigger particle collider because we need to measure H bar more accurately.
If you want a fun fact,
Yep.
You know H bar is a very low number.
Well, I mean, hold on. I don't remember them.
10 to the minus 34 or something.
Oh yeah.
Very small number. The extra, every loop you introduce also introduces an extra factor of H bar. And that's why every new order has very less contribution.
Oh, that is ridiculous. That's like way less. It's an understatement in that case, isn't it? If it's an extra.
No, well, if the integral is still diverging, then this small factor doesn't do anything.
I mean, yeah, exactly. So,
it depends on all the other content how much less of a contribution it is.
Make it. You must focus more on quality. You must focus on quality more than quantity. Brilliant.
Ouch.
Brilliant comment.
Yeah, make it.
Yeah, I do. Yeah, just of my recently common uploads and videos.
Yeah, you've been uploading every day. Oh wait, that's streams.
I've been uploading way too much. Time ordering. I like how the problems is like a single sentence.
I love it when problems are like that.
It's great. 4 fundamental forces.
I don't even understand the problem. Yes,
What do you have to say
gravitons.
about gravity, actually?
That's actually a good question, because in all the quantum field theories I've seen, gravity is excluded.
Such model
Because
is
it's
called
difficult.
unrenormalizable. Yeah.
Yeah,
Yes.
because if you introduce gravity, you can't add these counter terms
You know
anymore.
what's funny? In the video, I'm actually going to start with gravity, simply because it will be the only fundamental interaction that I can explain without quantum mechanics. I can just give gravity as an example of what the fundamental interaction is, and then right away go to electromagnetism for
What is a fundamental interaction then, in terms of gravity? Because if you are not saying gravitons interacting, then...
Oh no, it's effectively just there to explain what an interaction is.
Okay.
It's simply because if I don't say what an interaction is, then I'm gonna get to a weak interaction, and then it's gonna be honestly bitch to explain.
Weak interactions are best explained with Feynman diagrams.
Oh, I suppose actually, yeah, because we're doing. I suppose when it comes to Feynman diagrams, there really wouldn't be much of a difference between any of the 3 interactions, would there? They all look extremely similar.
Yes, the only difference between the interactions is then how the squiggly lines, what kind of properties they have. For example, a photon in electromagnetism can only have it needs to connect to 2 fermions. That's the only possible way a photon can interact. You can't have it interact with 3 fermions, for example. Whereas the Higgs boson can interact with 2 Higgs bosons. So that's 3 in total. The photon doesn't do that. So the differences between the interactions is just the difference on how you control the lines.
Hold on, because Timothy just added the comment, and I want them to elaborate on this. I would describe gravity as light, but that's electromagnetism. What do you mean by I want you to elaborate. I need to know what you mean by that.
The homotopy is not a kind of knot theory. I'm sorry to break it to you.
Thank goodness.
But I guess you could have emergent knot theory if you consider the right topologies for your homotopy.
By the way, Fake earlier said I'm making my first video on why I think theory of relativity sucks. What do you mean? Why do you think theory of relativity sucks?
Well, I can give a lot of reasons why it sucks. Does it fucking comply with quantum
You
field
just
theory?
fucking want the graviton. You can't. Light is an electromagnetic wave, is it not? It's in the wrong category.
Not categories.
Shut up! Not that kind of category. Timothy, you're just giving Remco a PTSD flashback to category theory.
These are triggers for me.
Light is in the wrong category. What do you mean it's in the wrong category? It's in the very correct category. Boson. That fits. Honestly, I would even argue that if you are trying to understand bosons, photons are as simple as it gets. Like, listen, if you're trying to understand carrier particles, or I mean, if you're trying to understand bosons, right? What else do you have? WZ, they come in pairs. What, the quark? Good, not quark, fucking gluon. Good luck with that. Graviton? That's just blabberings of drunk people. Higgs? Don't even get me started.
I still think the Higgs is the most drunk particle ever.
Higgs is...
The gravitons make more sense than the Higgs, and we found the Higgs.
Never... Okay. Yeah, but I was saying in terms of fundamental forces, gravity can't be light. Yeah, because light is a photon. It's electromagnetism. Yes, gravity is not electromagnetism. Theory of
I actually see...
Oh, okay. Theory of relativity sucks because it's not compatible with quantum mechanics. That's not a great argument, in my opinion, Fake Octopus. Because, like, okay, I want you to really realize something. Theories don't have to be perfect to be good. And the reason why it's not a great argument is because you can actually state it the other way around. You could say that quantum mechanics sucks because it's incompatible with relativity, if that's what you want. Both quantum mechanics and relativity are proven to be extremely accurate.
I mean, it depends on which you take as fundamental.
Yeah, exactly.
The other one sucks.
Yeah, exactly, but if you examine both of them in a vacuum, both of them work at the respective scales. We wouldn't have effectively all of modern chemistry without quantum mechanics, just like we wouldn't have anything at beyond human scales without relativity. Thanks for the joke. It took me a really long time, Timothy. I'm sorry. A while back ago, I had someone. No, I won't point fingers, but I had like a lot of people who had a deep misunderstanding of physics, and ever since then, I am having trouble recognizing jokes. I'm so sorry.
Don't consider it like a destruction of the joke. Consider it an attempt to help you.
No, what's this play for a second because it does not fit the USB-C port. That's kind of, yeah. Quantum mechanics is objectively more fundamental. Very much subjectively. Oh, buddy, you are about to get me riled up. What do you mean quantum mechanics is objectively more fundamental? In what way?
I tend to agree with that.
Yeah, but like relativity is... You don't even need a universe for relativity to be a very obvious axiom. Because without relativity, you need some frames of reference to be preferable over others. I'm not saying that relativity is more fundamental. All I'm saying is that it's really difficult to say that one of them is more fundamental because it's so subjective.
I mean, not entirely. My argument for this is that general relativity could be more of an emergent property rather than an axiom. Whereas quantum mechanics is very, very difficult to implement it as an emergent property.
I suppose that was... Okay. I mean, I see what you mean.
And that's simply because the scale. Like, you can't have emergent property on such a small scale, but like, relativity is sort of an emergent property by itself already. But it doesn't Like it will be very difficult. And this is basically what string theory and other theories that started quantum mechanics are doing.
To be damn sure that models that explain smaller things are more fundamental than models that explain bigger things.
Yeah, don't be damn sure about that.
But the relativity doesn't have to explain. That's, you see, kind of a biggie of the theory of everything is that, you know, you don't. Relativity doesn't actually have to explain. Listen, the last time I've heard, photons are pretty small. And they tend to, like, be included in relativity every now and then. There's a reason why Einstein felt so proud after discovering that light travels at the speed of light. Fucking got a Nobel Prize for that.
He did not get the Nobel Prize for that.
Yeah, I know.
Sad. But I see your point, Fake Octopus, but I wouldn't be damn sure about it.
I don't like that point. I don't like that point because...
I appreciate a point. It's a heroic point.
I don't like that point because... well, maybe I am just focusing on the wrong part of relativity, but to me... the biggest part of relativity is... it's gonna be sound great what I'm about to say. It's things being relative. And so, like, for example, okay, relativistic energy. Do you need great scale for relativistic energy?
What do you mean? Do you need a what skill?
Do you need large scales for relativistic energy to play a part?
Well, you need to be close to the speed of light, so yes,
Yeah, exactly.
I would say so.
But you don't need great scales. You just need to be close to the speed of light. Like a single photon is an elementary particle, but it still travels at the speed of light.
If you're talking about fermions or non-massive particles, then you will need high energy to get to this scale. So you will need a lot of relativistic energy to get to the scale of general relativity.
Wait, but you're saying for massless or particles with mass?
Massive.
I mean, yeah, but you know, it's about particles with mass. Come on.
Sure. Fake Octopus. If like I get your point, but there is something very fundamental about general relativity.
I get the
in that
not to go on.
In that time is not the way you should think about it, and this is at very conflict with general relativity. This is also not like a bigger thing because yes, GR describes the bigger scales of the universe, but the reasons why it does so is not because it's only acting on a big scale; it also acts on a small scale. Like the whole concept of time does not make sense in GR, and it's like a necessity in quantum mechanics.
My only problem with your point, Factopus, is that you said that relativity sucks, which it's that strikes a nerve with me for some reason. Like, no actual scientists worth their salt think that the theories they are presenting are like actually objectively true, simply because if they actually start saying that their theories are objectively true, then what other science is there to be done?
You have not spoken to string theorists yet.
No, actually, string theory is a brilliant point for that, Remco. Remco, you have spent most of your time actually not studying string theory, only studying quantum mechanics, right?
Yes.
And yet you would much rather prefer string theory.
No, I don't know what I'm doing there.
No, but what I mean is like the thing is, the reason why so many scientists are more interested in string theory is precisely because it would be better than quantum mechanics. Once string theory becomes the status quo, there's just going to be the next thing to fix the inaccuracies.
Well, that is the problem, because string theory is not verifiable. Not everyone. Like, a lot of people in string theory, a lot of physicists, are just already convinced that string theory is true. They're just working out to fix it. That's why string theory is very toxic at the moment.
I didn't know that. It's actually really worrying.
Yes, and this is also why I'm fucking careful with what I am studying, because I'm not going to be like that.
That's actually really worrying, because like that's not what science is meant to be.
No, and this is like the whole problem. It's taking all the funding. So like if you don't do string theory, you don't even have much of a chance of funding. you also like there's a couple main figures in string theory. One of them, Ed Witten, the most famous one. They if they focus on something, everyone in string theory will follow, or almost everyone. And if they, after like a year or two, say, okay, we can't find a solution to this, they focus on something else, they will just abandon whatever they're doing and they're going to focus again on what these leaders are doing. So it's very much like a cult behavior. They don't go to conferences of the other fields. They stay within their own refined group. If there are people from the other fields, they're not inviting other people from other fields to their conferences. If there are people, there's like this whole air or atmosphere of why are you here? You're in another field. So it's a very toxic field at the moment, and that's why I'm so fucking careful with everything.
That is really boring because that is the exact opposite of everything I like about science. And
Yes,
that's
agreed.
something I would expect from fucking, I don't know, politics, not science.
It's because like there has been two major breakthroughs, and they are so spectacular that surely string theory can't be wrong.
Okay, hold
But
on.
it could also just be mathematical coincidences.
Before carrying on, I just want to say to Fake Octopus, I'm making a video on why theory of relativity sucks as a model respecting its usefulness. Fake Octopus, I just don't like how strongly you're framing it, okay? Because in my personal opinion, when it comes to life after what Remco said, this is not gonna lie, I'm a bit less hopeful. But in my head, scientists are actually willing to change their mind in relation to evidence presented. And I genuinely don't think that there is a single scientist there is a single honest scientist who is doing good science whilst believing that what they are working on is truly ever elementary. Most of the time in science, we don't say that things are surely elementary, we just assume them to be elementary, and of course we do. Because if you don't want to assume elementary particles to be elementary, then good luck finding a model that fits. So what we do is we assume elementary particles to be elementary, whilst keeping in mind the fact that they could not be elementary. It's not as simple for them not to be elementary as it seems, considering you would need, well, the standard model to be wrong, quite something that would be. But still, we keep in mind that they may not be elementary, we assume that they are. And the same thing happens with relativity. When you use it, you obviously don't assume that it's correct because it can't be absolutely correct simply because it doesn't click with quantum mechanics. At the same time, it is a damn good model and it is incredibly creative. But yeah, that's just one thing, quick break, because I just don't like, there's this whole thing I don't like with when the misunderstanding people have of science, which I think is the source of all of the toxicity against science, is that there's this sort of assumption that scientists think that they are correct all the time, which is the opposite of what science is. The whole point why we're doing science is because we think we're wrong. If you think you are correct about something, you wouldn't need to test it.
Yeah, this is applicable on everyone but string theorists.
Yeah, and the whole reason why I think that there's a mistrust of scientists is because there are also a lot of people, scientists out there. That's why the video is going to be titled "Why Theory of Relativity Sucks" and not "Why Physicists Who Model it Sucks." Yeah, but the theory doesn't suck. It's really good.
I actually am very curious. If you have your video out, title me. I am a sucker for hot takes.
Because but in this case, I just don't like how charged this hot take is, because the negative, so far from my understanding, the main underarching reason why the theory of relativity sucks, in this case, is that it isn't a theory of everything. Which, a lot of theories are gonna suck if we apply that to them. Relativity is... I am a big fan of relativity. I think it's incredibly creative.
I'm less of a big fan of relativity.
I really am, simply because Einstein's dealer simply did a lot of amazing work, and that's just... But yeah, I was not aware of the string theory issue like that at all. That is truly worrying and horrifying.
Yep.
My goodness.
There's also a lot of like there's some conjectures in string theory, and most people have just like already taken them as truth. Like, and there's no active research on it anymore, like proving it. Sure, there are some people working on it, but there's not actively like with the group or with with some physicists that are just proving these conjectures. No, we'll just take them as truth. So, not too exciting to go into theory. Let's just say that. But the material is really cool, and the techniques are also very, very useful. So I'm doing this for myself.
I mean, if you go into string theory, you don't have to join the cult.
Exactly.
You can be a voice of reason. That's something.
That's what I'm saying to myself.
You can do the research, and if someone misinterprets your research, then you can come to me, and I can make a video shaming them. That's it.
Oh, brilliant. Not only do I have my own publisher, I also have my own trash talker.
Symbiotic relationship. What do you think publishers do? But that's the job of a publisher, being a trash talker. That's the point.
Love that. I am curious about the video Fake Octopus, though. I'm curious about the arguments.
I am worried about... I think we need to avoid, like... we're talking about scientific things. We need to avoid making them too like emotional and charged with strong language by saying that something sucks, etc.
Great, but if the arguments are good, then there is a valid way of... Like, I can say that like the theory is trash because I have arguments that it doesn't exist.
Yeah, but even then, it's better to say incorrect than to say trash. Because the thing is...
Yeah, okay, fair point. I see your point there.
That's my point in this case.
Yeah.
Like, if the video would be titled something like, why relativity doesn't work, for example, or why relativity doesn't work with quantum mechanics, to be even more specific.
Yeah,
that would be just extremely accurate.
I suppose your entire argument is to don't put the emotions into...
Yeah, because a lot of people, will... Okay, Fake Octopus, allow me to just give you the full reason, because I've been kind of skimming about it. A while back ago, on my channel, I had a person in my comments section of one of my videos go on a rant and reply to a bunch of other people because they didn't believe that relativity was real. Now, when I say that they didn't believe that relativity was real, I don't mean that they didn't think that, relativity, that they believe that relativity was inaccurate or something. No. They thought that Newtonian mechanics, like classical mechanics, were better than relativity. And that Newton's explanation of gravity was better than relativity. They had a channel on which they made videos titled stuff like Why Relativity Sucks. And I have watched those videos, and the arguments weren't great. One of the most notable ones is that one of the arguments they proposed is that no one explained relativity well to them, and whenever they would ask questions, they would just be insulted. And I am worried that a lot of people like that would see a video like yours and simply because of the title completely misinterpret it in order to support their point. Being responsible while making videos is important. You did a video about relativity, was the 4 horsemen of the universe. 4 horsemen of the universe included gravity, but... Oh, wait, what video did they comment under? I, didn't... This is still wild I haven't made a single video about relativity, but I do mention it a bunch. It could have been...
We should work on that after Feynman diagrams.
I keep putting of relativity, because relativity is a... I've already mentioned it before as well. Minute Physics did such an incredible explanation of relativity that I just feel bad making my own video on it.
Well, we're going to make a video on it.
Because, I mean, they've made such a... It's such a great model. It's incredible. Hold on, let me find it. It was so incredible.
Hey, promoting can only happen in the promotion channel.
Oh, wait, what happened? There's something.
No, you're promoting Minute Physics.
Oh, I mean... Shut up. Okay, Minute Physics Relativity. It's this one. Intro to Special Relativity, I think, was it? Lorentz transformations, there. This video...
Oh, yes.
It's so brilliant. because this is such a confusing part of relativity, and they just made the model that explains it so well with the physical object right here. And I mean, how do I beat that?
Well, you don't have to beat it. You can give your own version.
But I don't have my own version, that's the issue.
Well,
Like for...
you don't have your own version about Feynman diagrams right now as well.
No, for Feynman diagrams and such, I can actually, because what I want to do for Feynman diagrams is that you always see Feynman diagrams as static images, right? And what I want to do is I want to do Feynman diagrams from, so first show the Feynman diagram, then have like a vertical, like a horizontal line going bottom to top to show how it's going over time, and then have like a horizontal, and then have like a slice of the same interaction with particles but without the underlying Feynman diagram, to make the connection that, you know, Feynman diagrams represent actual particles.
Ooh, that's good.
Yeah, exactly. See, I'm actually trying to...
I see. That's good. You should still add the mathematics though.
Obviously, I'm gonna add the mathematics. The entire beginning, the intro to the video will be chapter 5.1. This will be the introduction to the video, simply because I feel like it's a great motivator for why we think of elementary particles as particles. so this will be effectively like one of the first frames of the video will be this equation, which I'm certain will not make any people click off the video.
No. People are very interested in that equation.
It does suck. Fake octopus. Now, let's go from better models. I just don't know what to tell you at this point, fake octopus, because I just really like relativity. It's brilliant.
No, I will need proper arguments, not saying it sucks.
Yeah, in 100 years.
As a model, it is one of the most celebrated models because it has verified the most experiments.
Exactly.
So every experiment from general relativity has been... Wait, not everyone. Like there has been four separate examples of experiments that were confirmed by general relativity that were not confirmed by Newtonian physics. One of them is the... how was it called? The ethereal motion of Mercury or something. There has also been gravitational lensing, which is entirely not explained by Newtonian or any of the other models, I might add, any of the post-Newtonian models. There is, just black hole. Nothing with Newtonian talks about or supports even the motion of a black hole. So you can't just say general relativity is trash, because without... Give me one more example, actually. GPS. Can't do that with Newtonian physics.
That's always the example I bring up, because, like, what I said earlier, that everything at human and greater scales. Like, it's hard to say that relativity sucks when basically the modern internet would just most likely not work in the current setting without general relativity.
I always like to phrase it as you are framing your arguments against relativity using devices that's entirely built upon relativity.
Yeah, exactly. It's the same thing as we had with Terta, right? Where there was someone random who said that quantum mechanics sucked. Well, it's funny for you to say that quantum mechanics sucks, considering how your computer wouldn't function if we didn't have quantum mechanics.
Yes, exactly.
Wireless communication wouldn't be able to function without relativity. If we haven't accounted for relativity, to be more exact, more specific.
Yes, and this, you can just say that like this is the principle, or this is the principle of how was it called again? No, I forgot its name. The principle of equivalence.
That's the gravitational mass to motion mass?
Yes, the principle of equivalence, which I think is a very natural one, and the principle of relativity, which is just photon mass stays the same, whereas like if you move, then your time just rotates into your space. So those two very humble assumptions, may I add so, they naturally imply general relativity. You don't need to do anything else. You just have these two basic assumptions, and from this, general relativity follows.
Hold on, I feel like we could start with actually simpler question. Something exact the modern theory can be useful, you know? Fake Octopus, what is your experience with relativity? What experience do you have with it? Because relativity is one of the more advanced parts of physics, and the thing about advanced parts of physics is that they tend to be counterintuitive. Same goes with quantum field theory. The more advanced you go, the more counterintuitive everything gets. It's kind of the reason why it's advanced. So what is your experience with relativity? Because what I'm saying is that it's not only useful, but also on a theoretical basis, it's very impressive. I had experience with it. My teacher never taught it properly to me.
Well, then perhaps that might be one of the reasons why you don't see its value.
When you see your teacher at what level of education? I'm so sorry for questioning you in that way, Fake Octopus, but I do believe it's important. Masters. I see. That's not bad. That's not bad. All matter just. Hold on.
The whole, like, it being sucks as a model, but it can still be useful. I agree with a lot of models that this is the case. Like, they can predict stuff, and this can be verified or not verified. And the model might still suck because some properties are just not showing, or it defies some other experiments, or the mathematics is not elegant, or something, blah blah. But with general relativity, there is no like counter experiment that denies relativity if you don't consider quantum mechanics. And even if you consider quantum mechanics, there is still just experience that we don't know its answer to, just nothing denying general relativity. But if you're in your masters, so you have seen the mathematics, it's all step-by-step derivation. You don't need any other assumption. General relativity just stems from these two assumptions. If you have these two assumptions, you get general relativity for free. The whole problem is you need to pick your own model, and you need to pick your there's not one single solution to the Einstein equations. Yes, and that is making it seem more as a theory of theories. But so is quantum field theory, because you don't have your field theory doesn't have like a given Lagrangian. You need to input your own Lagrangian, and this is technically also a solution to some larger equation. So I don't really know where GR sucks. Or should suck. Yeah, I will want to see the video. But I am kind of agreeing with Make It.
I think Fake Octopus in this case, there is an underlying point to be made there, which would be interesting, but I think you are far too biased to deliver it. It seems like you just had a really bad experience with relativity, and you are making your video as more of a grievance and less of an educational material, simply because you're trying to vent negativity towards relativity. That's at least that's at least what I get from conversing with you right now. I think if you actually focused on just the difficulties of making the theory of everything and the places where quantum mechanics does not work with relativity, that would have been actually genuinely interesting. But I think you clearly don't like relativity, and it shows. And that's a problem, because you can't really let those sort of things bias you. I would know. Listen, there are plenty of things I absolutely hate with a capital H in science. Don't even get me started on the moles and how idiotic they are as a unit. But in this case,
Biased.
yeah, I'm biased because they're idiotic. I hate them, burning passion. Also, that is true for every field. Not quite immoral, actually. Not quite. I would argue that the more theoretical you get, then that starts becoming a case where basically advanced topics become counterintuitive. But the less theoretical you get, then that's no longer true. So, for example, with I don't know, solid state chemistry. I'm gonna butcher it a bit because solid state chemistry is quite a wide field. But once you get more advanced and start specifically, or material science more specifically, once you start focusing on materials, then you don't get. They don't just become universally more counterintuitive. They just become more advanced. Simply because for a lot of materials you don't have a good intuition for what they should do in the first place. Or medicine would be an even easier example, right? In medicine, as you keep going, things aren't becoming more and more counterintuitive, there's just more and more information. But in physics, things are actually becoming more and more counterintuitive simply because things that are intuitive and we consider true are taught on the very beginning because, well, they are intuitive. Oh yeah, object with more mass is harder to push. That is quite intuitive to most people, hence why it's one of the first things you learn. This
Oh, by the way, fake octopus. If you are interested, we can talk over this. Not because I want to convince you otherwise. If you believe it, you have reasons to believe it. But I want to know those reasons. I want to think on those reasons. Because for all we know, you could be right, but for all you know, you could be wrong as well.
No, I mean, in this case, I feel like fake octopus is obviously right on that, relativity isn't the perfect theory. Like, that's obviously right.
Excuse you. I think it's perfect. I think quantum mechanics is just a hoax.
They may have the particles. I think one of my videos just stopped doing quantum mechanics. Hold on. But I just think in this case, fake octopus has a fair bit of bias, and that worries me.
I mean, in physics, most of the Nobel Prize winners had some kind of bias because you need a bias to find something like counterintuitive / extraordinary.
Yeah, but you
don't. Yeah, but it wasn't on the scale of theories.
No, what I mean is that you're in when someone gets a Nobel Prize, they get a Nobel Prize because they replace a worse theory with a better theory, not because they just say that the worst theory is worse, right?
Mm-hmm. Yeah, but if you have a reason why this theory doesn't work, and you start thinking about ways of showing that it doesn't work, and then you experiment on those things, and you're actually proven right, that is a very biased way of finding physics. But it's not the conventional way of doing physics, don't worry.
It's actually kind of funny to me that in this meme they chose the Feynman diagram instead of expanding it into the actual equation. Would have hit so much harder. No, it's brilliant because, okay, the way I'm gonna start the video is... This video will be riddled with asterisk because there is no way I'm going to actually explain all of the particle physics in depth, simply because I just don't have a budget for that. But the way I'm gonna start it is with the Hamiltonian, right? I'm just gonna show this equation. I'm going to say, this equation, and I'm going to say that this effectively means the energy of our, I should probably call it system, that might be better. Energy of our system is equal to relativistic energy of our system, which is equal to quantum mechanical energy of our system. And the whole reason why I'm stating it this way is because then I'm going to use that. Right away, I'm going to say it's an asterisk because what the fuck does quantum mechanical energy even mean? Just made it up on the spot. And then the reason why I'm going to say that is because then this will be as a setup that a relativistic energy doesn't exactly work with quantum mechanics, which will then allow me to skim over all of this mathematics, because it's a lot, and just end up right here in order to state the point that if you have a field, how should I phrase this? If you have a Dirac field, that would be just field of electrons, positrons, correct?
Yes.
Yeah, so...
Well, I think I'm not familiar with the phrase Dirac field. But yes, probably.
Dirac is easy check. Dirac field. Fields half fermion spin.
Yeah, okay, so it's just oh, I see. Makes sense.
An example of spin half fermion field is Dirac field.
It's just a fermion. It describes the spinors. So spinors are Dirac fields, apparently.
Okay, so in this case I could just say that that would be oh my goodness, this is very loop-de-loop. The easiest way to explain why we treat particles as particles is to explain that we treat them as quantized fields. But in order to explain why we treat them as quantized fields, I would first need to showcase them as fields, and for that I would need to explain why treating particles as fields is even... So basically, the easiest way for me to explain this would be to say that we have particles, and we effectively treat these particles as fields. This is meant to be like a two-dimensional grid, and these fields, we treat them as quantized fields. So effectively, we treat them as particles. It's idiotic. This video, the start of the video is gonna be rough.
The Holy Trinity.
I don't know where to start this, because like, it's incredible that you can... Well, maybe incredible. It's very like illuminating to have a field for particles, a quantized, and then it's incredibly illuminating to have that field be quantized. But the intuition is already for particles.
Quantum mechanics. Yeah. Well, you will have to think of them as sort of excitations. Like this is the same with the particle-wave duality. You can't think of particles as point-like objects. Doesn't work.
To simplify quite a lot of topics.
What could help, especially in the beginning when you show that one equation, the top equation, you could give the Newtonian counterpart.
I mean, yeah, I suppose that's fair. It's just like energy.
It's just p squared divided by 2m.
Yeah.
And that is the energy. So that's what you're doing, basically.
In this case, I could say that the Hamiltonian would be kind of like 1/2. Because, okay, then psi would be kind of like mv, right? Because the formation of a particle.
Wait, what would be mv?
Psi.
Squared?
No, not mv squared, only mv would be kind of like the psi, and the operator would be kind of like 1/2 mv squared. Am I making any sense with this? So...
No, I don't think your psi is...
No, what I mean in this case,
Yeah.
not. I know that psi isn't momentum, but I mean that like psi is there to represent the information about our particle.
Yes.
And so in this case, the m and v variables on their own are there because they convey the information about our object in classical mechanics. So like the variables m and v, that's the information, and then hold on, let me just I need to draw it out for this to make sense. So like, you know, if we have like function for getting the energy, kinetic energy of our particle, then it would look like this.
Yes.
1/2 mv squared, and then this function would be kind of like the Hamiltonian operator, and then these variables that we plug into them would be kind of like psi.
I see what you're going for.
Am I making sense with this, or am I not? I know that's a
I see where you're going for. I wouldn't take it as is. Like, yes, the
Alright.
function including its arguments is exactly the Hamiltonian. But the whole problem is in Newtonian physics we don't need the psi, so we can just like divide out by psi on both sides because you're not dealing with operators. So there is no psi in Newtonian physics. There is
that's
no.
True. I mean, I can just say it's energy because I mean Hamiltonian times it's, and I'm just gonna label it like with the word energy and it will make sense.
Keep in mind that the right hand side, the I h bar partial derivatives to the time, is also exactly the energy.
Yeah, I know. That's in this case I'm calling it the quantum mechanical energy.
Yes.
So it
I
will,
like that space
it
actually.
will be energy, relativistic energy, and quantum mechanical energy. And each time I'm going over them is I'm gonna say energy over system, and when I say system, it's gonna highlight the psi on each and every one of them. So energy over
Yes.
system, relativistic energy over system, then quantum mechanical energy over system. Okay, topic none of this video will be coherent. So I'm going to link the textbook I've used for this in the description in case you'd like to learn more. And in the meantime, let's keep going. Right away, we run into an issue, and in this case, as I say this, the Hamiltonian and equality is gonna just vanish. I'm just gonna push it to the side, and I'm going to be left only with relativistic and quantum mechanical. And
Yes.
as we're left with them, right, you run into the issue, and then I need to explain the fact that this doesn't work.
Bad.
The issue, the elephant in the room, and that is that despite them being equal, by definition, they are both energies, and coherent models should always have the same energy, because obviously it doesn't make sense for relativistic energy to be different than quantum mechanical energy, because they're both effectively just energy, they have to be the same. So despite them being equal, this equality, I shouldn't say it doesn't hold. Instead, I should say it's problematic, right? Because the whole...
It's not defined. Like, taking the square root is not defined on its own. You will need to Taylor respond to define it anyways.
That's because of the square root. Okay. Could you run by me the Taylor expansion once again? Because in my head, I still just have the two solutions, and I'm having a hard time getting it out.
The whole thing is, like, for example, if you have an operator, which is just a matrix, think of it as a matrix. If you square this matrix, it will be just applying the matrix twice.
Yes.
Yes. If you exponent the matrix, you will get the Taylor expansion of the exponent, where you just plug in the matrix, where you would normally have the variable. Wait,
so plug the matrix into the matrix.
Yeah, look up the Taylor expansion of the exponential.
Of the what?
Exponential. EX, e to the power x.
Right.
Yes, that one. So what you usually do is the right-hand side, you define e to the power of a operator. You define it as the left-hand side, you define e to the power of an operator to be 1 plus the operator divided by 1 plus the operator squared divided by 2 plus the operator cubed divided by 3, etc. Right. So the left-hand side is defined in terms of the right-hand side for an operator.
Right.
You will do exactly the same with the square root, because it doesn't make sense to talk about the square root of an operator. What is the square root of a matrix? This operation is not defined for matrices. So now look up the Taylor expansion for 1 plus x, or the square root of 1 plus x. You do know that the Taylor is with a Y.
Okay, close enough.
Yes. So once again, what you're doing here is you define the square root of 1 plus an operator in terms of this series expansion. And the reason we have 1 plus an operator is because if we go to our relativistic energy Hamiltonian stuff, then you see that the m squared c fourth is constant, so it's not an operator, whereas the p squared is the actual operator here.
Right.
So if you divide out the m squared c squared, you will get something like 1. Well, you will get in front of the square root, you will get mc squared.
Square root of 1 plus x with some constants.
Yes, and in this case, yeah, exactly. So you define it as the right-hand side.
Mm-hmm.
But this means that the energy of the system, so the IH bar partial derivative to t, is equal to, p divided by 2 times some constant, minus p squared divided by 8 for some constant, plus p cubed divided by 16, etc., etc. But p is basically just derivative to time, as in the line above, the derivative operator. Wait, with respect to space, of course. So this means that your energy depends on all the possible derivatives of some space component of the wave function. This means that your energy depends on all possible it depends on the entire space, because you can take the derivative of an operator always depends on multiple coordinates.
So you basically, in order to evaluate it, you would need like an infinite amount of points to figure out what that power would be.
Yes, and that is, first of all, it's non-local. Second of all, if you now try to assume the principles of relativity, which basically say space and time need to be on equal footing. On the right-hand side, you have the energy, just one derivative of time. On the left-hand side, the square root is a sum of all derivatives of space. So they're not even like on the same footing anymore. And it's horrible.
Which means that derivative change in relation to time is equal to changes in relation to, I know it, okay, to like time and time chain and time, like time velocity. That doesn't make any fucking sense, I know. But like time acceleration, time jerk, all these things.
Well, in terms of space, then, yeah.
No, what I mean is like, time equivalent of velocity. I know the time equivalent of velocity doesn't make sense, but listen. Basically, the derivative in relation to time is equal to all orders of derivatives in relation to time.
No, in relation to space.
In relation to space, sorry.
Yes. In that case, yes. And that is horrible. Because one, relativity is not a debate anymore. You need time and space on equal footing. And second, it's non-local. Your energy depends on, like, your energy of a particle at position X depends on the available energy, for example, in Andromeda galaxy. So in this equation, you will need to consider the entire energy of the entire universe to be able to calculate the energy of your particle.
Oh, that does make sense.
And it's not fun.
Okay, so
that makes no sense.
It's not exactly. So it's not exactly wrong. It's just unusable, like to the extreme degree unusable.
I mean, it's also wrong because it's not relativistic, and you want.
Oh yeah, and also that, yeah. That's on top.
And at least, like, you can use it as a model. It's just it doesn't represent anything physically. Like, it's first of all not relativistic. Second of all, you want your physics to be local because you want to be able to define your energy. Like if you like look around the particle, you don't want to consider something that's happening at the other side of the effect, because not only is that non-local, it also violates once again relativity because information travel light. So if something at the Andromeda directly affects the energy of the particle, that is non-relativistic once again.
Okay, so if you try to use this equation, you will find that in order to find the energy of your system, you just need only two things. First, the information, first, all information about the entire universe you are in, and secondly, you need to break a couple of fundamental rules of relativity in order to calculate relativistic energy. This is problematic.
Slightly.
That's actually a brilliant way to put it.
Amazing.
If you want to combine together quantum mechanics and relativity, you just need to break a couple of fundamental rules of relativity to get relativistic energy. Megan, suppose that you're given node A and B, which are two vectors, and then another vector CA cross product C is equal to B, then what is C? I'm not great with linear algebra, Moral, I'll be honest. Examples outside of the universe, actually. Why can information not travel faster than speed of light? I do have to say though, the example is outside of our universe. If there is something outside of a universe in that case, that would be included.
Outside of a universe is not defined.
That's kind of like the supernatural, the word supernatural. It's just the word itself is the word itself is just doesn't make any sense.
Yes. Or something like before time.
Yeah, exactly. That's another great one, yeah.
The amount of questions I've had, what happens before the Big Bang? Fuck you mean before the Big Bang?
Long before time had a name. Or long before time existed in that case. It vexes me so much when in different science fiction you get like, oh, you know, this being exists in a dimension without time. What do you mean? We've been there.
It's static.
I think Doctor Change had that where Dormammu, like the dimension of Dormammu didn't have time. And like, what do you mean? Dormammu can talk. In order for you to talk, something needs to change. Oh, it's changing in respect to what? I'm sorry. It vexes me. It vexes me as well.
Yes. It gets even crazier when you consider two types of time.
I mean, because if you don't have time, then change as a concept breaks away, because then you would need to have change in relation. All of our change in our universe, we treat as change in relation to time. That's the point. Point of time.
Yeah, except you need to be careful with saying such things because of relativity.
Oh yeah, as always, relativity.
What the fuck is time?
But relativity still changes space-time, right? Like,
yes,
time is still a crucial component there. It's just not special anymore.
Yeah, exactly. You can all in every system you can define some sense of a time direction or time axis.
Strangely
it's just not the same for. Yeah.
So strangely uses time stone to go back in time in the Ramos dimension. You don't even need to go that far. The things are moving in there. All right. I'm getting oddly worked up about this. I don't know why. Well, I get your point. You really want every movie to be directed by Neil deGrasse Tyson, but that's such a simple change. Instead of saying that there is no time in that dimension, just don't say that, because there is clearly time. I know. How do I know? Because he went there and he spent some time over there. I know. Just say that time is independent. That would be something. That would be something. That would actually be a brilliant point. If you have a dimension where would just like time is completely independent to the time in our dimension, that would be interesting. I'm getting the same thing as happened. I am very obsessive. I have an extremely obsessive personality, and that's why I remember these things. Just like I remember in the first Avengers movie, there was a point where they are fighting on Stark Tower, and over there was the scepter, and they're trying to get the scepter, but they can't. And one of the characters says, "Oh yeah, the scepter. This is a barrier of pure energy." And I'm flipping out like, "What do you mean pure energy?" It's just a bunch of energons, the particles of energy, you know.
Energons.
Yeah, energon. You know, the particles of energy. They have all the energy.
And you say physicists can't name shit.
No, that's not what they said. Like that's. But what do you mean by barrier of pure energy? What is that supposed to be? Light?
I guess I could see something.
I mean, well, I don't know. Light, gluons, any boson of any kind. I could any particle, I guess. Anything. Fucking glass.
You could translate that to available energy, I think. So all of the energy is being able to be used, but that doesn't define particles. Particles don't like that.
Still mean anything. In this barrier of pure energy. How is that a barrier?
Well, if you try to get through it, all the available energy will interact with you, basically annihilating it. You're welcome.
Yeah, but that would just be... I'm getting oddly worked up about this, okay?
Yes.
Maggie, I think you're the kind of person who I think I could enjoy a fantasy magic system made by you. I am just very obsessive on these sort of things. Like my
energy is not just a property of matter. If only. That would simplify so many things.
What is matter?
What is energy?
No, genuinely, this is a genuine question. Like, what does matter from point of view physics? Because
Matter?
Like, yeah, is it just mass? Things with mass?
No.
Then what is
because
matter?
Photons are also matter.
So photons are matter. Oh, that's curious. So wait, what is matter then? Just stuff.
I guess if you want to define matter in the framework of general relativity, you would define it as the stuff that arises from the energy stress tensor. You're welcome.
What if matter is a property of energy? Alright, Einstein.
The whole thing why I say that energy is not just a property of matter is because I don't think dark energy is matter. Because it's more of a tendency of the universe to act. So it's more like energy of space-time itself, and this is not matter.
I like that what Dark said though. What if matter is a property of energy? Because there was this one guy, I don't remember who it was, like in some kind of physicist, I don't remember exactly, but they did say like E equals mc squared, and that would track certainly. I don't remember who was it though.
What if matter is a property of energy? You know what? That's a crazy wild take. Hold the fuck up.
Wait till you measure. Oh wait, what was the unit there? Electron volts per speed of light squared. If I remember, that's the unit. Electron volts per speed of light squared. Is that the unit?
Which one?
A unit of mass that you really often use with particles. EV by C
EV.
squared. There we go.
Yeah, no, the C squared is 1. Don't care about that. Yeah, it's just EV.
It's a pretty unit. Oh, shut up! Oh, I'm gonna strangle you. Yeah, that's
No,
shut you
just
up.
tell us.
That wasn't even. It's my dishwasher.
Oh.
My theory is all magic. Yeah, the physicist lobby trying to convince me that energy isn't matter. No. The Higgs field is totally not just the arcane might of a couple of wizards who sacrifice themselves in order to grant us all just an unreasonable amount of mana potions. That's lies.
Lies and slander.
Exactly. What is
Neither
dark
truth
energy?
nor
I have
slander.
no and or very minimal knowledge of this topic, so yeah, there is no way for me to have the proper conversation. I think you understand
Yeah.
it perfectly well, actually. I would say based on what you say, Immoral, I would say that you get what dark energy is.
Well, let him write the paper. We are curious as physicists.
I mean, he, Immoral did just say, I have no and or very minimal knowledge on this topic, which is like, that's kind of it, isn't it? That's like spot on when it comes to dark energy.
Yes. Yeah, exactly. It's just that.
Yeah, I mean, you got
Nothing
it.
else. Good work on you, Immoral. Good work. You are ready to become a physicist.
This is funny though, because like that genuinely is about it. That's why it's called dark.
My theory is that it's all magic. Yes. In a sense, yes.
Complicated mathematics, and we'll end up with these two vectors. Wow, these are suspiciously simple. And that's because they effectively say that, and how am I gonna slice this cake? Okay.
Oh, if you want the full answer, they just base vectors of a four-dimensional vector space.
Yeah, but for some reason, I feel like, an average person watching the video might not find that intuitive.
Huh. Well, that's a visual demo, I suppose.
Yeah, but the whole point of it is just to fix the skill issue, right?
No.
This coffee is working for me. I haven't been drinking quite as much because I didn't have the coffee pressy thingy, and now that I made myself just one cup, it's really keeping me going. Okay. So the spin up down. Should show the deal solutions.
I'm not gonna lie, these streams with coffee is such a vibe.
It is great, isn't it? Just
I have missed your physics streams.
I've missed them too. There's gonna be a whole lot more because you know that when it comes to the video we've talked about yesterday, I am going to be working on it on streams most of the time. So that will,
Yeah.
and that will just be me, unless you know the share paper publicly.
But yeah, still. More physics streams is definitely a
No,
pro.
like, are you ready to share the paper publicly or not yet?
Not at the moment. We still
All
work
right.
tonight
Then
and then refine everything.
I'll leave it out from the streams for now. But when you are ready, I would just do.
Oh yeah, I forgot I sent you the manuscript. Don't do it yet. No,
Don't worry, I won't. Don't worry, I wouldn't do it without permission.
we can't let the secret go away yet. We
Yeah.
can't let the secret escape.
For those who don't know, Remco and a couple of other people have like a little pet project of taking over the world, and they have like a paper detailing in honestly shocking detail, step by step, how to do that sort of thing.
Yeah, we're getting paid to make it.
You would be surprised just how important Subway is to the plan. It's considering it's just it's a sandwich chain. It's honestly surprising how crucial it is. But well,
Wait, I think there's a misconception. When we say subway, we actually mean the metro.
oh, then I got it all wrong. I misunderstood it.
Have you skipped over the preliminaries again?
I might need to take out the funds of a couple of things. I may have already set some things in motions, and well, that's whoops.
You know what? Never mind. We can change the plan.
Subway will work.
Subway will work. Either of them will work. There is a minor plan. They will play a large role, but they don't know it yet.
What is the coffee pressy thingy? Oh, you didn't see the coffee pressy thingy. Oh, damn it, I need to turn on my camera just to show off the coffee pressy thingy. And the even worse bit is that my camera is set to such comically low levels of like... There we go. I know it's really dark, but I don't have the patience to actually turn on the lights again. It's this. It's like a thingy that you put coffee in and then you press it down so that you don't get the dirt. The coffee dirt in your cup.
I like the coffee dirt.
Yeah, I personally prefer to eat it separately.
Ah, fair. You should make the like whenever you turn on the camera, but there's no active imaging yet. You should make that a rainbow instead of the stripes of colors. Or actually, just an entirely white screen also works, but that's maybe a bit evil.
That would be actually surprisingly annoying to do. I would need to set up a script that detects if there are actually pixels, because that's the easiest way to see. I would need to make a script that detects if the pixels on the screen are the stripes. That's because the stripes you see is my video capture card sending data that there is no data. So, you know, kind of letting my PC know that it's connected, but nothing is connected to it. So I would need to...
Yeah, you need to override that, I see.
Would still be doable with enough time and patience and, well, insanity, alcohol, anything is doable.
Not yet. Problem for later.
Because my electrons and positrons are a natural way to compose the Dirac field. This is the general solution of the Dirac equation. Okay, how do I slice this cake once again? Basically, these are suspiciously simple. Say that in our universe have a field. So basically a value at each point. And these values can either be this vector or this vector. Or in other words, a spin up lepton. I always mistake leptons for fermions. Was it lepton or was it fermion?
I would not even know what a lepton means. It's something like electron, surely.
It's fermion. Shit! I know. On the very beginning, I confused fermions with leptons, and now I confuse leptons with fermions.
Just forget about leptons. Fuck the leptons.
Oh, was this a spin-up fermion? Whilst this is a spin-down fermion. Actually, wait, hold on. Are these... Which one is spin-up, which one is spin-down?
It doesn't matter. It's like plus or minus, but I would
this is just
usually
particle. Maybe I should say particle.
Yeah. But like, it needs to be a spin half particle, I think. So it needs to be a fermion. Yeah. Like, go at the beginning of the entire paper or whatever this is called, like the lecture, because I think they are saying something like, oh no, they don't say it. I think this is for a fermion though.
Hold on. This next is for spinless particles, but not describe fermions. Okay, so this equation works for spinless or spin 1, but everything that goes down is for spin half.
Yeah. Okay, so it is
Fermions.
fermions. Spin half particles.
Spin down fermion. And this is where we'll begin today's video. A crazy ride. Don't worry. Here's where things will slow down. And then I'm actually going to change the structure completely because I just realized that this will not work. Instead, we're going to do it differently. We're going to do fermions and then photons. So fermions will be, but without neutrinos. Wait, no, leptons in this case. Shit, leptons without
Why leptons?
neutrinos. Is it not leptons? Hold on, leptons.
Leptons without neutrinos is just electron, muon, and tau.
Yes, that is.
But I doubt you even mention muon and tau because fuck muon and tau.
No, I do need to in this case. If I'm doing, you know, I should do the whole standard model, right?
Fair.
I mean, it's the reason why I want to mention muon and tau is because it's a really nice setup for weak interaction later down the line.
Yeah, that's fair.
I make a ethanol mix with petrol good for the environment when used as fuel for vehicles. That's a curious question. I would say that ethanol mixed with petrol isn't all that crazy different from just petrol. simply because they're both effectively just carbon chains. I mean, ethanol. Alright, so as far as I'm aware, now take this with a grain of salt because I'm not an environmental scientist, so I cannot tell you what effect it has on the environment. All I can tell you is the chemistry. The thing is, the reason why carbon chains like just emitting carbon dioxide so much after the reaction is because carbon dioxide has a very low energy in comparison to the chain itself. So basically, transitioning from any kind of chain into carbon dioxide yields a big difference in energy, which is why we get so much carbon dioxide out. Now, we don't get only carbon dioxide out, we also get a bunch of other things. And in this case, if you look at ethanol and burning ethanol, I'm pretty certain it results in the same thing. Hold on, burning ethanol reaction. I looked into it a while back ago for something. Yeah, CO2 and water. So I don't think it would be all that different from petrol. I mean, petrol... I think burning petrol also results in carbon dioxide. I don't see why it wouldn't. The whole oxidizing bit is really easy to do with oxygen. Alright, first leptons. Electrons. So, what is an electron? Well, considering how this is a video about particle physics, you could be tempted to think that electron is a particle. And I mean, you're not wrong. Wrong. It is certainly a particle, but in this case, we'd rather think of them as, would it be an, not perturbation, only, what's the proper name for it? Excitation?
If you're talking to me, I will want you to rephrase your question.
I mean, I was asking it to myself, actually asking you, but is electron an excitation in the field when it comes to quantum field theory?
Yeah.
Okay.
Yeah.
Alright. We'd rather think of them as excitations in field. So basically, imagine our entire universe as being one-dimensional. In this universe, you could even... Oh, the graphics for this could be so incredible. Because then I could actually... Like, adding an electron could actually... I could actually show it as a wave. And if I do it right, I could even do it with some really good mathematics to have it, like, appear. That would be neat. Petrol has impurities. Yes, because it's effectively just a mix of all the different carbon chains you can find. There's no point in separating them because they all burn roughly the same.
I will have to go for now.
It's fine. I appreciate you helping me out so much.
It's fun. If you have more questions, I'll ask them through chat or keep them for when I'm back.
If I have any question, I will be sure to ask or compile them. Thank you so much again, Remco.
Yes. Good luck with the rest. I believe in you.
Cheers, I'll need it. See ya.
Yes. Ciao, ciao.
Okay. Oh, in the meantime, that just reminded me of something. This animation, I completely just left it, haven't I? Yeah, this is breaking a bit, but that's simply because the cache of the Premiere file is a bit messy, so hold on, let me just fix it. Ah. How are you all doing, by the way? Because, you know, you've been joining and I didn't even ask. How rude of me. How are you all doing? Balin, Immoral, Dark, Timothy? How are all of your days going? there we go. And there we go. Then what we'll need to do is we'll also need to increase the brightness. There we go, this right here. And then geometry nodes. Day is pretty good, you know. Hold on. Bless me. And day is getting pretty good. In the 1 week break between summer classes and college starting. Are you excited for college? Because if you are, then good for you. And also nice that you have a break. I'm glad that you're enjoying your break here with me. Okay, and then what we need is we need to slightly dim the lights. So let's just dim them down to like 1000. I think that should be fair. I'm glad that I brighten up the lights just to dim them instantly. Let's see if we can see the difference in colors. No, I already started college summer classes and more college classes. Oh, I see. I'm sorry, I misunderstood then. Oh, so you're in between. So you're basically on a 1 week break between college and college. Great, that's good. Well, I hope you like studying what you're studying, at least. How high of a brightness do I need to set it up as? Because this is ridiculous. Oh, I think we might not have enough samples. No, you can roughly see the colors now. You can see that this is slightly bluish, this is reddish, this is greenish. But the floor just isn't reflecting it. Oh gosh, oh golly. Oh great. We might need to also take the glass and make it transparent for this. Mix, shader, and transparent. Or translucent actually? No, transparent. Yeah, that's it. That's what I had to do. And now we can dim it back down because, my goodness, this is still a lot. I think 100 might actually do it, the trick. Let's see. Alright. Yeah, brilliant. That's exactly the kind of look I was going for. The only question is, because there is a slight possibility that at the halfway point it could be just overwhelming. Let's see. I made the mistake of thinking that the summer upper division math class meant it would be easy. Well, this is over now. Do the colors on your logo represent anything? Kind of, but it's boring, so I don't really get into it much. In this case, we'll need it to disappear almost instantly. 1, 2, 3, 4. And then 100, and hopefully this will crazy. Right here we can actually delete this. Yeah, it instantly kind of flashes on the very beginning, but then it should be fine. Oh, and even better. Oh, that would be even better if I could pull it off. Okay, yeah, if I could pull it off, that would be even better. But basically, if I take all of these texts right here, if I take them, then they all have... Oh, damn it. Don't worry, we'll be back to particle physics in a second. Just give me a second, I need to fix the animation. Right here, if I add realize instances, there we go. and then object apply visual transforms? No, object apply there we go. Apply this, and then oh, this is gonna be annoying. Basically, what we need is RGBs, and then we're gonna have RGB 1, 2, 3. This is gonna be the first one. RGB 001. Okay. Then this move right here. G.002 and then B002. Brilliant. And then one last one, which is this. I don't know why there are so many G's, honestly. G003 and then B. Brilliant. And then the reason why we did that is because what we're effectively going to do is object info. Was there a way to get object by name? Damn it. String. Object, no. Damn it, I do believe there was a way to get object by name. Not Python, geometry nodes. Is there really no way? You can get instants, not instantly, you can get attributes by name. You cannot get objects by name. Fine, that will make the process significantly more annoying, but fine. See if I care. Right here, we're gonna turn this off now. And then R1, G1, B1. There we go. Like this, like this, like this. Well, that's a problem. Because that really should have appeared them. How did it appear them in the middle? No. Sorry, where is the object at? G, B. Okay, it does appear in the middle. If I do relative. Aha, got it. Right, it's brilliant. That's because now what we can do is we can actually store named attribute of brightness. And then we can just take... Oh my goodness. Just set material. Set to white. And why are you off now? Alpha. There we go. 0. Brilliant. Okay, that is exactly what we wanted. And then we just take this, math, divide by 4. There we go. And the reason why this would be better is because now, if we just repeat the process for all of them, then as they change their underlying colors, then at the same time these calls on the top will change brightness, which means that as the animation goes on, there we go. You can see that the first one that's emitting red light gets really high, really bright R and really dim green and blue. This one gets really dim red, gets really bright green, side dimmer blue, and there we go. Ah, render animation, finally. I'm not getting the difference. All Matter art is really funny. All Matter is great, aren't they? Absolutely brilliant. Hold on, let me actually hard. Did I hard this? Oh, it's probably easy, but I'm gonna hard it as well. Alright, that's brilliant. What's next on our agenda? This. Right, this can you imagine being one dimensional? One dimensional. So just a singular line. You can go right or left. Or wrong. Right or wrong. Those are the only two options. For now, I'm modeling it as having no particles. So this is just an empty universe. Right? Well, not quite. Because even though we have no particles, we still have something remaining. The line itself, the field. This field is important. Oh, no, I just got a message on my phone. Let me see what it is. Uh-oh. The field. The field is important because the action of us adding the particle is just excitation in the field, like this. This right here is an electron. Replace artists, but seeing Omat's arts, I know they won't. They can't. That's what I'm saying. Reaction. There we go. All right. Like this right here is an electron. It's effectively. Where do I go from here? Where do I go from here? Where do I go from here? That's a good question. Effectively, the psi you see in all the equations. The psi refers to this function, that function in this wave. And that is the big idea behind quantum mechanics. Yada, yada, yada. I've made too many videos about that already. What we'll focus on today is particle physics, however. So basically, we have this excitation. Then what we'll do is we just say that this excitation is a particle. So when you hear a particle, you might be tempted to imagine it as a point or a ball. And yeah, that's how I'll be representing it as well throughout this video for simplicity's sake. But in reality, this is what particles are. They are excitations in their fields. Rather, that's what they are in quantum field theory. The process of that this excitation in a particle is effectively quantization, hence the name. Now, with this electron in mind, actually maybe I shouldn't cover leptons quite yet. Maybe let's just go electrons. Let's add another one. There we go. We have 2 electrons. Lovely. Now let's bring them closer together, and oh, would you look at that? We've got a bond from the past episodes of this series. Isn't that lovely? What's bond in chemistry effectively is just this. These 2 functions affecting each other. So interacting together so effectively. Interacting together. Yeah, that's kind of it. Now where do I go from there? I don't want to retrace too many steps I've already been on. So instead, the new voice-to-text feature on the mask, you should be able to voice and script the video at the same time. What do you mean, just say it out loud and have it be recorded? I could actually do that, but it's hard to explain. The reason why I like putting it in text is because the main issue with the video making process is that it's not too difficult to have ideas for a video, but like there are a lot of different variables at play, let's just say. So basically, I know that there are a lot of links I could make. I could start with electrons and then move on to electromagnetism, move on to photons. What I could also do is start with photons as the massless particle, and then I could expand it through quantum mechanics and the addition to mass to all the particles, and as such, and as such. That will make the script pointless. I'm an idiot. No, that is something. Because, I mean, effectively right now, I am saying out loud exactly what I'm scripting. So I get your idea. But in this case, it's just, I would need to turn off the audio feature too often for this to work. These 2 functions affecting each other, so interacting together. As mentioned, I've already covered the past episodes of this series, so steps. What I haven't covered, however, is interaction between different means. For example, they both have charge, them repelling each other. And here's where we get to the second chapter, photons. Before we get, however, let's take a look at our elementary bingo. In this bingo, we have 17 particles and 4 interactions, which in our current models we consider to be elementary. We can already fill in electrons. Next, it's time to add electromagnetism and photons. As you might have guessed, the fact that electrons have charge means that they must interact through electromagnetism. Basically, they are able to repel each other. And even though we find that behavior obvious and intuitive, I mean, we've all seen magnets, it's worth asking another question. How could that happen? I mean, how could they interact at a distance like that? Is it magic? Is it divine intervention? Is it just a bug in the simulation that is our universe? Well, no. In quantum field theory, damn it, why am I struggling so much with typing? Field theory, we have a simple-ish explanation, and that is quantum fields. So think about this way. When we had our 2 electrons come together and interact, they were still effectively interacting at a distance. The difference being that distance. Hi there, how you doing?
Greetings.
Do you have some time?
Sure, I can make some minutes. I just wanted to say that divine intervention might probably be the way.
Okay, never
I
mind.
do it on a regular basis.
I was just going to ask for a quick clarification if my thinking is correct.
Yeah, of course.
So in this case, all right, I'll be quick. In this case, I'm trying to model a one-dimensional universe, and effectively what I'm doing is, with the example of a single electron, it will look something like this, right? Where this will be continuously oscillating back and forth, and this will be like a single electron. Then with 2 electrons, it will look something like this, right? So far, okay. Then with 2 electrons interacting together, they will just be like, well, I'll just add the waves together. So this, and then the big one that I'm not quite so certain about, which is with the photon. With the photon, what I want to do is I want to have the 2 electrons like this, still at the distance, and then I want to add another field, this time the electromagnetic field, which would look like this, to explain their interaction. Is that a fair representation? This being the virtual photon that pushes them apart.
Yes. If you get, I mean, let me think about this. I think this suffices for the current presentation. Because the one issue with this is that these excitations are usually in K space, so in momentum space.
I see, that
Which
that would be difficult to represent.
yeah. So I think if you represent it like this, it will be fine.
Okay, I'm just gonna add the asterisk then.
Yeah, like it's still a momentum space, so it's a bit difficult to like. That's why this whole particle to wave duality is so conceptually confusing. But yes, that is how I think about them.
With the electron field, I'm just gonna call it electron field for simplicity's sake, and I'm just gonna add another asterisk. What would a zero-dimensional universe look like? Just one particle whose energy, position, or time never change. The zero-dimensional universe would just be a point with a value. It's... I don't even know if you would call that a particle. That would just be a point. Like, even in our... We like to think of particles as points, because it's, well, simplifies a whole lot. But even particles aren't points. The whole universe being a point is... You wouldn't
Useful,
even
actually.
effectively have much of a field, would you? You would just have like a value.
Wait, let me rephrase the stuff I'm doing in my thesis, the melanification, etc. This is in the framework of a 0 plus 1 dimensional space.
0 plus 1, so it's...
Only time.
Only time, I see.
And the reason why is because you're integrating out all the
Wait.
position. So there is no positional dependence, so you only have time dependence.
Oh. Right.
I don't understand it either yet.
Yeah, because to me...
it makes no sense.
To me, zero-dimensional would have to completely change it, because then you couldn't have a wave bucket, could you?
I mean,
with time you can.
apparently you can.
I mean, you know, like I don't know, relativity, time, position was the difference. Wave bucket's a wave bucket.
Exactly.
Propagates through time, propagates through space, so big deal. This time they cannot interact with the electron field because...
But the main reason I joined, I don't have access to chat for some reason. I get an error whenever I send a message.
Oh, that's
I was saying that a positon with positive charge and an electron with negative charge, you don't expect them to repulse because charges, like you expect them to get close to each other because of the charges. So it's not that concise to talk about repulsion in this case.
No, because the reason why I'm talking about repulsion is because I'm going to have two electrons at a distance, and the whole point is that I want to show them that they interact without the usage of the electron field. So, you know, on the electron field, I don't know, Dirac, whatever. On the electron field between them right here, this will be flat, right? So,
yeah.
So the question is, how do they interact at a
you...
distance? And the reason why they interact at a distance is because there is another field that interacts with them, and that is the electromagnetic, which actually does do something between them.
Keep in mind that in this presentation, the photon is not... It doesn't fill all the space in between. It will be a photon package propagating from one electron to the other.
Oh, so I should have it like this, and then just bouncing left, right, left, right.
You just need this to go, yeah. No, it's just one interaction.
Yeah,
you need this to move slowly to the right.
I know, but I'm going to have it bounce left, right, simply for the sake, because I want it to, you know, for everyone to understand. Because if it just goes once, that could be unclear. I'm gonna asterisk again. But I really like this representation, though. I feel like that kind of representation of fields could clarify it really well.
There is one thing I haven't talked about with Feynman diagrams, which is... Hold up, let me pull up the whiteboard.
Of electromagnetism, which means that what we need is another field. The electromagnetic field carries the electromagnetic interaction, and the reason why they repel at a distance is because in this electromagnetic field is where the repulsion happens. Okay, let me just join the whiteboard.
this diagram, the electron positron repulsion, is actually just a shorthand for this. So the photon propagating from the left electron towards the right electron, and it's also representing the other way around.
So like this one is just a superposition of these two.
Yeah, so this technically, even though this is equal time, so it doesn't say between which one it propagates, it needs to propagate from one electron to the other, or the other way around.
Yeah, so this one
yeah.
is flat, not because it's like literally takes no time, only because since it happens at the speed of light, we might as well like simplify it to say that it's flat.
No, the whole thing is that these two diagrams contribute equally. So it doesn't matter which one, which propagates and which receives.
Okay.
Both of these are equally valid. I don't think we can even measure it because these photons are virtual. And this, actually, you should be able to. No, you can't measure it. This time scale is also negligible. So it really doesn't matter which of the way you consider. So you just write them as if it's just instantaneous.
All right. Let me think how I can work with them.
So in that case, you could have this bouncing between this and then this bouncing back. That's just different. That's just adding a line, adding a line, adding a line.
That's because these electrons can actually interact with this electromagnetic field. So one of the electrons... Oh, I think I have an idea. So one of the... So effectively, the interaction starts with one of the electrons causing an excitation in the electromagnetic field. Then this excitation travels at the speed of light, nice foreshadowing here, to the other electron, which then causes them to repel. Now, which of the two electrons causes the excitation? The left one? The right one? Well, both. And neither. And only one. And the two. If that makes sense. Which it shouldn't. Shouldn't. Because it doesn't. Superposition! There we go, brilliant. That should explain everything. And then I'm just gonna have for half a second on the screen, I'm just gonna have a flash of text that says it is actually superposition of both of them happening at the same time. No, that shouldn't be both of them happening at the same time. Both of these could potentially happen, so it is a superposition of both of them. Something along these lines.
You can't verify which of the two happens.
Yes.
Because they're virtual photons.
This covers the electromagnetism of the standard model. But I did also promise a particle. And so, where is that particle? Well, right here. Just like electron is an excitation in its field, photon is an excitation in the electromagnetic field. So, and that's why it's called the carrier particle of electromagnetism. It carries the interaction between particles.
Do
Okay.
you have any other questions?
I don't think so for now. But yeah, I don't think so.
Alright, I will be
Alright.
heating away then.
Good luck. See ya.
You too. Ciao, ciao.
Oh, how convenient this to have Remco, honestly. I will need to credit Remco with this video, because it's already been... He's already helped me a lot. Okay. Now right here what we need is this. And right here what we need is to get rectangles, cubes, you know. We truly have a scalar universe. Okay. 3. Make this smaller. This. Actually, let me just join them. Actually, no. Before I join them together, this one has to be at -2.5, and then this one has to be on the other side. Now we can. We shouldn't join them together either. We should give them the white. Yes. I downloaded Physical Physics. No, I'm not. I'm just taking a brief break in order to work on the animation. Stored attribute, brightness, e-color. There we go. 1 and right here 1 6, and then what we do is we just keep this, right, brilliant, this and this. And now we can clear their positions, that's not exactly needed, and then we can just bring them ever slightly lower, like this. Brilliant. Is the Particle Physics next video after the mask? It might actually come out before the mask video, because the mask video is taking a lot out of me. Between the particles. What else? Oh yeah. There are 2 kinds of photons you can encounter. First one is just light. So basically, you know, light. That's just a bunch of excitations in the electric field. I don't think there is much I need to explain there. The second kind is one I just covered right now, and that is the virtual photon. The reason why it's called virtual is because since we cannot actually measure. Does the mask ever speak to you like Green Goblin mask? If so, what does it say? No. What? What do you even mean by that? Just like the speak to me? No. That would be weird, though. Why would it speak to you? What does it speak to you? Okay, that's weird talk. Where did you even hear that, huh? Who told you that? Who told you that? They're lying. Don't listen to them. It doesn't, okay? It doesn't. Shut up. Just shut up. Doesn't. Okay? It's not telling me to do anything, alright? And even if they're not exactly crimes, like, okay, listen. It depends on the jurisdiction. It's, you know what? It doesn't matter. The point, that's relevant. We're working the video. We're working the video right now. Because since we cannot actually measure, these photons, they start at one of the electrons and go to the other. There is no way to capture halfway through. The only reason we assume them to exist is because there has to be something carrying the interaction. Once again, in the quantum field theory, we theorize them to be a quantized field. Simple. Next, we'd have, actually hold on. Good question. Muons. How does particle physics treat muons? Are they on the same field? Hold on, lepton field. Hi there, Ashquanta, how you doing? Lepton, electromagnetic interaction, no, I'm looking for... this is going to be tricky, isn't it? Where is the textbook? Okay. In this case, let's read leptons, because we want them from the perspective of particle physics and quantum mechanics. How are they treated? I'm making a video of particle and stuff, right? Yes, I am, in fact. Electron muons, yes. Okay, now quantum chromodynamics really too far. Radically modern introduction to physics. Okay. The standard model, yes. Oh, this is tricky. Does anyone watching the stream happen to maybe know, I don't know, why, if all leptons exist on the same quantized field, or if they have separate quantized fields? Fermionic field, wait, hold on. Fermionic field is quantum mechanics whose quanta are fermions. Ha! Fermionic fields obey canonical anti-commutation relations. Are they kind of... Okay. Oh, all of them are the same. Dirac field. Okay. Alright, brilliant. Dirac field. Dirac theory of an electron, yes. Sounds lovely. So far we have been using which are limited to describing non-physical particles. Point track from the Hamilton that describe electrons being close to the speed of light, so the combining quantum features special to be an with drag series that actually predict magnetic movements of the electron. Okay. Yes, spin. Okay. This we've kind of been over already. This is just the expansion of all the mathematics that go into the alpha and beta. Actually, no, halfway through it changes something different. Oh yeah, positrons, right, that's what it changes to. That makes sense. Electromagnetic quantizing. Alright, let me see. This is tricky. Actually, 7 and 8 chapter in this case could give us the... What is scattering theory? Well, I'm assuming theory of scattering. Scattering is... How to explain it? Are you familiar with Feynman diagrams? That would make this... No, 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 damn it. No. Scattering is effectively kind of like particles changing. It's the easiest way, changing to interactions. The easiest way I can explain it, or interactions to particles. No, interactions are particles. I'm not explaining it well. I'm sorry. The point is, it's like to oversimplify it a bit. When particle changes into another, it's an oversimplification. But right now, I'm still thinking about this. Strange particles. Please tell me that's it. Strangeness. Did Flame answer my question? First of all, you did not spell their name correctly. But no. I spelled particles. Summarize the questions about the broken symmetry. Okay, back to Fermi-electrons then. The equation was a drag equation where the gamma h is endless mass. Simple possible solution is the equation is plane wave solution. Plane wave solution based on Fourier exponent along the general expansion of the wave function as follows. You have an experience level spin area. For the energy factors, the result of having Lorentz invariant integration measure. In second quantization, from what is the operator coefficients for you. Yeah, okay. In a manner analogous to non-relativistic annihilation and creation operators that communicates these are related to the interpretation. Oh, jeez. More complicated field theories involving interactions. It's not exactly what I was looking for. What's the actual name? It's... Are you on Discord, Complex Thing? Are you on my Discord server? Okay, quanta of fermions. That's the issue though. I do have a question for Remco actually that I might need answering. Hold on, let me ping Remco. Remco. When it comes to muons tau, are they excitations on the same field as electrons? So are all fermions excitations on the same field? I think it's difficult to find the answer to that. Unless I'm an idiot. Possible. Color symmetry, flavor symmetries. Okay. Randomly dipped. Welcome back, Ash. Why are you on edge? Ooh, physics stack exchange, that could be good. It doesn't know about quarks and leptons, it knows about bosonic and fermionic fields. In quantum theory, the standard model of particle physics is the framework of specific context. Okay. But the basic idea is essentially yes. Each different type of fundamental particle is an excitation of its own field. Alright. Never mind. You're not. Okay. I'm not sure if I want to say that here or not. If you're not sure, better not say. I respect it. I understand. Okay. There's going to be quantized field. Simple. I'm learning about particle near the electron in the 16 or 70 particles. What do you mean? Am I learning about particle into electron? I had a specific question, which is that are muons and tau, or all leptons in general, excitations on the same field as the electron, which they are not. Works. I think quarks would come next then. What you're doing and whatnot. Exactly. That's the spirit, Ash. Workalism. Okay, in that case we do need flavors. There are one physical concepts mentioned in spinning dynamics system of variant symmetry transformation. There's a theorem, one of the most important female mathematicians of this century. For equal symmetry, there is a concept quantity. Okay, symmetry, spherical symmetry. Okay. And difference that it's mass. Not even close. One of the most common conditions which is realistic as well to know it's launch frame. The group of launch transmission can be decomposed into two ways. Boost from the launch velocity rotations where we change the orientation of the coordinate frame. Okay. Reduce space, space-time. Many particles carry the spin of the particle to form total angular momentum. Alright. Parity's transformation will reflect each point in the origin. Should be familiar to you. Okay. Harmonic oscillators wave functions, right. One-dimensional harmonic oscillator Hamiltonian. It does not change under substitution. The well-known eigenoscillator is probably even or odd parity. Right. We say that the state has even parity for the minus sign, which we go negative parity. These are only individual eigenvalues. As can be seen from looking at the probability density, since it must be invariant, we find that this, which shows that the only real eigenvalues we have is -1. It can show the relation between parity and momentum column. It is one, however, that the parity has an intrinsic power, which is particle form and negative parity which field. Originally, it's with fancy electrons behaves exactly the same way as a similar set of positrons, so we change the sign of the same. Actually, the symmetry generalizes a little bit, and general refers to transformation where we change all particles into antiparticles. Okay. It's not apparent. Damn it. Sign. Slightly nastier. Nice for space now. Space. Okay. Right. CP theorem. I don't think this is exactly what would help me. Or CP violation. Continuous symmetries. Alright, very important group of associations is related color carried by the quarks. Very basic the transformation within SU3 are all those amongst vector consisting of three complex objects that conserve the length of the vector. These are all 3x3 unitary matrices which act on the complex vector psi by this. These complex conjugate vector can be shown to transform as this. With the inverse of the matrix, clearly the fundamental presentation of the group, where the matrices representing the transformation are just the matrix transformations, the vectors have length 3. The representation is usually labeled by its number of base elements as 3. The one that transforms under the inverse matrix is usually denoted by power 3. That the inner product of psi and z is scalar. Oh, right. I don't think symmetry is what I'm looking for. Symmetry group symmetry like I said, superfine prestige and particular the symmetry summarized in table 7.11.1. Alright. Okay. Strange particles. Gimme. Once again, observe new particles in cosmic ray events. Cosmic rays were the tool before accelerator existed. They are just yeah, okay. Unfortunately, the number of highly energetic particles is very low, and they won't see new events. These particles come into forms: a neutral one that decayed into plus minus, and positively charged one that decayed into plus. Okay, the photon. Right. They live. There are many cases fun. For a second, decay dimensions about -10, much more difficult. Okay, many similar particles have been found within the collecting of strange particles. Actually, using accelerators, it was found that strange particles are typically formed in pairs. This mechanism was called association production, or suggested about difficult quantities such as charge called strangeness. If we assume that strangeness -1 plus 1, this balances out. Okay. Weak decay does not conserve strangeness, conserves the baryon number. It is indeed found to take much longer. Okay. We get particle with visualized identifiers, which agrees the fact that there is no particles of different charge and similar mass and strong interaction properties. Okay. Oh, this is rough. These are unfortunately too big for particles that we're talking about. There's new particles come with flavors called up, down, and strange. And assume that the baryons are made from 3 of such particles. The mesons from quarks and quark. Each of these quarks carries 1/3 a unit of a baryon number. The probabilities can now be tabulated. Okay, so this is effectively there to... Right. I think I found a way to slice this cake. Effectively, I can just start by introducing the quark. From the quark, I would go to the strong interaction and gluons. This will be very similar to the way I talk about the electromagnetism and electrons, so that would be nice. Then from there, we can talk about baryons, and we can talk about different combinations of baryons, how many there are, and then how we need to combine them. I'm exhausted. It's been 3 hours of solid work, and I am exhausted. So I'm gonna go now. I'm gonna have dinner. I'm going to, hopefully this time, finish the chapter of the video that we've been rendering in the background throughout the stream. And then I'll be honest, I'll either be with another live stream or I'll just end the day by working some more. But I hope you enjoyed this physics live stream. It was fun. And for now, that'll be it. Thank you so much for watching and have a great day. Bye.